Why the sky is blue. Rayleigh scattering of sunlight. You've probably looked up at the sky thousands of times and thought nothing of it. It's just blue, right? Normal, boring, predictable blue. But hold up a second. Isn't that kind of weird? Think about it. Water in a glass looks clear. Air itself is invisible. Space is black. So why in the world does the empty air above us glow like someone painted the whole ceiling with blue paint? This question has been bugging humans for centuries. Ancient Greeks thought the sky was a reflection of the ocean. Other cultures believed it was the dome of heaven, literally painted blue by the gods. And honestly, if you didn't know the science, those explanations don't sound too crazy. But here's where the real answer comes in. And spoiler, it has nothing to do with oceans or gods. The real reason the sky is blue is something called Rayleigh scattering. And don't worry, that name sounds intimidating, but it's actually super simple once you picture it. Imagine sunlight as a big box of colored pencils. Inside that box, you've got red, orange, yellow, green, blue, indigo, violet, all the colors of the rainbow. Normally, when they're all together, they just look white to our eyes. That's why the sun looks white or yellowish. But when that sunlight enters Earth's atmosphere, it doesn't stay neat and tidy. The air acts like a bunch of tiny obstacles, molecules of nitrogen and oxygen, that start smacking the light around. Here's the cool part. Not all colors of light get scattered the same way. Think of it like a mosh pit. The shorter, tinier wavelengths, like blue and violet, get tossed around way more than the big, lazy red wavelengths. Red light is like the tall guy in the crowd who just keeps walking straight, barely pushed around. Blue light is like the small kid getting bounced in every direction. So what happens? The whole sky fills up with blue light from every angle, and that's what you see when you look up. Now, you might be wondering, wait, if blue and violet scatter the most, why isn't the sky violet instead? Good catch. That's because our eyes aren't very good at seeing violet compared to blue. Our eyes are tuned to blue more strongly. Plus, a lot of violet gets absorbed higher up in the atmosphere, so blue wins the popularity contest. But here's a mind bender. The sky isn't always blue. At sunset and sunrise, it turns red, orange, and pink. That's the same physics in action. When the sun is low on the horizon, the light has to travel through more atmosphere. By the time it reaches you, almost all the blue light has been scattered away. What's left? The tougher, longer wavelengths like red and orange. That's why sunsets look like fire paintings stretched across the horizon. Want another fun fact? This isn't universal. On Mars, for example, the sky is often reddish during the day, but at sunset, it turns blue, totally backwards from Earth. That happens because Martian dust scatters light differently than our atmosphere does. So if you ever find yourself standing on Mars one day, you'll see blue sunsets instead of red ones. How cool is that? And here's a little myth buster. The ocean is not blue because it reflects the sky. It's the other way around. The sky is blue because of scattering, and oceans look blue mostly because water itself absorbs red light. Reflection plays a small role, but the main reason is totally separate. So the next time someone says the ocean is just reflecting the sky, you can flex with the real answer. Think about how wild this is. Every time you look up at the sky, you're not actually seeing blue air. You're seeing sunlight that has been shaken up, scattered, and filtered by millions of air molecules. It's basically space graffiti, painted by physics, and we live under it every single day without even realizing. So the next time you're outside and you catch yourself staring at a bright blue sky, don't just think, nice weather. Realize you're actually looking at the fingerprint of light itself, broken apart by the atmosphere. A reminder that even the simplest, most ordinary things around us are hiding a layer of cosmic magic. Why the ocean looks blue, not clear. Here's something you've probably never really thought about. If you scoop up a glass of ocean water, it looks pretty much clear. Totally see-through, nothing special. But when you stand on the beach and stare out at the horizon, the whole thing looks like a giant sheet of deep blue glass. Sometimes it even shifts into turquoise or greenish shades. So what gives? How can something that's basically invisible up close suddenly turn into this endless blue blanket when there's a lot of it? For a long time, people assumed the ocean was blue just because it reflected the color of the sky. And I get it. That kind of makes sense. The sky is blue. The water's surface is shiny, so maybe it's just like a mirror. But here's the twist. That explanation is mostly wrong. Reflection plays a little role, but the real answer is hidden in the way light interacts with water itself. Let's start with light. Sunlight looks white to us, but is actually a mix of all colors: red, orange, yellow, green, blue, indigo, violet. When white light shines into the ocean, something interesting happens. Water doesn't treat every color equally. Water has this habit of eating colors from the red side of the spectrum first. Red, orange, and yellow wavelengths get absorbed really quickly as light travels through water. Green hangs on a little longer. But blue? Blue is like the last survivor. It travels the farthest. So when you look out over the ocean, what you're really seeing is sunlight that has lost its reds and yellows along the way. The leftovers, the colors that remain strong enough to scatter back to your eyes, are the blues. That's why the ocean looks blue. Here's an easy way to picture it. Imagine you're at a party with a bunch of snacks lined up. Chips, red, cookies, orange, cupcakes, yellow, candy, green, and finally lollipops, blue. As the night goes on, people eat the chips first, then the cookies, then the cupcakes. By the end, the only thing left on the table is the lollipops. So when someone walks in late, they're like, wow, I guess this party is all about lollipops. That's basically what happens with sunlight in the ocean. Red gets eaten first, and blue is what's left behind for us to see. Now, you might be wondering, if the ocean swallows up red light, does that mean everything underwater looks different? Yep, that's why scuba divers bring special flashlights. If you dive deep enough without extra light, red colors basically disappear. A red fish might look dark brown or even black at depth because the red wavelengths never make it down there. Shine a flashlight, and boom, the fish suddenly looks bright red again. It's like magic, but it's just physics. And here's something fun. The ocean doesn't always look the same shade of blue. Sometimes it's turquoise, sometimes dark navy, sometimes even green. That happens because of a few factors: depth, the angle of sunlight, and stuff floating in the water. Shallow water near beaches often looks turquoise because the light bounces off sand and coral underneath,
mixing with the blue that's already there. Areas with a lot of plankton or algae can look greenish because those tiny organisms absorb and scatter light differently. Want a little mind bender? On rare occasions, in certain places, the ocean can even look reddish or pinkish. That usually happens when there's a bloom of microorganisms, like red algae, that literally change the color of the water. So yeah, the ocean's mood lighting isn't just about reflection or depth, it's also about who's living in it. But let's circle back. The big mythbuster here is that the ocean is not simply a giant mirror for the sky. If it were, the ocean would look gray on a cloudy day, but even then, it still often looks blue or green. That's because the color is baked into the way water itself absorbs and scatters light. So next time you're standing by the sea, take a second to think about what you're actually seeing. You're not looking at blue water. You're looking at sunlight that's been filtered, stripped of its reds, and sent back to you in shades of blue. It's basically the ocean showing you its personal light trick. And honestly, that makes the ocean even cooler. It's not just a giant puddle of H2O. It's a massive, living filter that transforms plain white sunlight into a shifting canvas of blues and greens. Which means every time you stare out at the water, you're not just looking at a pretty view. You're watching physics in action, playing out on the biggest stage on Earth.
How rainbows actually form. Rainbows are one of those things that feel almost too magical to be real. You're driving after a storm, the clouds are breaking up, and suddenly, bam, there it is, this huge arc of colors stretched across the sky like nature just whipped out a paintbrush. Kids point at them, adults take pictures of them, and somewhere in the back of your mind, you might even wonder, okay, but seriously, what is that thing? Why does the sky just decide to bend into a giant neon smile after it rains? Now, the old legends gave us some fun answers. Leprechauns hiding pots of gold, bridges to heaven, signs from the gods, you name it. But the real explanation is actually way cooler, because a rainbow isn't really out there in the sky. It's happening in millions of tiny water droplets all around you. And once you know how it works, you'll never look at a rainbow the same way again. So here's the simple version. A rainbow is just sunlight getting bent, bounced, and spread out by raindrops. That's it. 3 steps: refraction, reflection, dispersion. But let's break that down into human terms, because refraction doesn't exactly sound like a word you'd use at dinner. Imagine you're driving a toy car across a smooth table, and then the car suddenly hits a patch of carpet. The front wheels slow down while the back wheels are still on the table, so the car veers off at an angle. That's basically what happens to light when it enters a raindrop. Sunlight is traveling fast through air, then it hits the water droplet and boom, it slows down and bends. That's refraction. Next step. Some of that bent light travels inside the droplet and hits the back wall of it. And what does it do? It bounces, like hitting a mirror. That's the reflection part. Then the light heads back out the front of the droplet, bending again as it exits. So each little raindrop is like a tiny disco ball for sunlight, bending and reflecting light in just the right way. But here's where it gets beautiful. Sunlight is made up of all colors mixed together. When light bends inside the droplet, the different colors don't all bend equally. Red light bends less, violet bends more, and everything else falls in between.
This spreading out of colors is called dispersion. That's why you don't just see plain white light shooting out of raindrops. You see a whole gradient of colors, separated like slices of a pizza. Now, here's the fun part. A rainbow isn't really a physical thing hanging in the sky. It's not like you could fly to the end of it and touch it. A rainbow only exists because of the exact angle between you, the sun, and the raindrops. Specifically, the light that makes a rainbow usually leaves the raindrop at about 42 degrees for red and 40 degrees for violet. That means the rainbow you see is unique to you. Someone standing just a few feet away is actually seeing their own rainbow from a slightly different set of raindrops. It's like a custom light show just for your eyes. And that's why you can never find the end of the rainbow. The closer you walk to it, the more the angle shifts and the rainbow basically moves with you. It's like chasing a hologram. You'll never catch it because it only exists from your point of view. But wait, we've got more rainbow tricks up nature's sleeve. Sometimes, if conditions are just right, you'll see a second, fainter rainbow above the first one. That's caused by light bouncing twice inside the raindrops before exiting. Here's the kicker. The colors are reversed in the second rainbow. Red is on the bottom, violet on top. And between the two rainbows, there's usually a dark gap called Alexander's band. It's like the rainbow has its own special effects department. And then there are even rarer kinds, moonbows, which are rainbows formed by moonlight instead of sunlight. Super faint, but totally real. There are also fog bows, which happen when tiny droplets in fog scatter light. They look white and ghostly, like a rainbow in black and white. Here's one more thing to melt your brain. A rainbow isn't really an arc at all. It's a full circle. From the ground, you only ever see the top half because the earth blocks the rest. But if you're in an airplane and look down at the right angle, you can actually see a full circular rainbow beneath you. Imagine looking out the window and seeing a perfect glowing ring in the clouds. So the next time you spot a rainbow, remember, you're not just looking at pretty colors. You're seeing sunlight bending, bouncing, and spreading inside millions of tiny raindrops, each one working like a little prism. And the rainbow you're looking at, that one's yours. No one else is seeing the exact same version. It's physics wearing its most magical disguise.
Why stars twinkle, but planets don't. You've probably been outside at night, looked up at the sky, and noticed something kind of magical. Stars twinkle. They shimmer, flicker, and almost seem alive, like tiny diamonds constantly winking at you. It's one of those things we just accept as pretty. But have you ever stopped to wonder why? And here's the real kicker. If you look closely, planets don't twinkle in the same way. They shine steady, calm, almost smug, while stars look like they're throwing a dance party. What's going on up there? The answer isn't about the stars or planets themselves. It's about the messy, chaotic layer of air we live under, our atmosphere. Think of Earth's atmosphere like a giant swimming pool of moving air, full of bubbles, currents, and temperature differences. That's what causes stars to twinkle. Atmospheric turbulence. Here's how it works. Stars are so far away that by the time their light reaches Earth, it's basically traveling as a single super thin beam from a single point. When that beam of starlight enters Earth's atmosphere, it has to pass through miles of shifting air, layers of hot and cold, dense and less dense, all moving around. Each little pocket of air bends the light slightly, kind of like wobbly glass in a window. The result? That tiny beam of light is constantly being nudged in different directions. To your eyes, it looks like the star is flickering on and off, changing brightness or even shifting colors. Twinkle, twinkle, little star? Yep, that's literally the atmosphere messing with your view. Now compare that to planets. Planets are much closer than stars. Millions of miles away, sure, but not trillions. Because they're closer, planets don't appear as a single pinpoint of light. They actually take up a tiny disk in the sky. It's so small your eyes can't resolve the details, but it's just big enough that when their light passes through the atmosphere, it doesn't all get bent the same way. Some parts might shimmer one way, other parts another, but it all averages out. Instead of flickering, planets look like they're glowing steadily. Basically, planets are like sturdy candles, while stars are like little sparks dancing in the wind. Here's a quick analogy. Imagine you're looking at a lighthouse far away across the ocean. If it's just one sharp pinpoint of light, the waves in the air or water might make it seem like it's flashing on and off. But if you're looking at a big, broad bonfire, even with waves in the way, you'll still see a steady glow. That's the difference between stars and planets. There's another cool twist. The twinkle is actually worse when a star is closer to the horizon. Why? Because the light has to pass through more atmosphere, like trying to see through the bottom of a swimming pool instead of just the top layer. That's also why stars near the horizon sometimes seem to flash wild colors, red, blue, green. Your atmosphere is basically turning into a natural prism, splitting the light randomly as it bounces around. Astronomers have known about this problem forever, and they even have a name for the twinkling effect, stellar scintillation, which sounds fancy, but it really just means stars sparkle. And while it's beautiful for stargazers, it's super annoying if you're trying to do science. If you're an astronomer trying to take a crisp picture of a star, the atmosphere ruins it by smearing and flickering the light. That's why telescopes on Earth can only get so sharp before things get blurry. So how do scientists get around this? 2 clever tricks. 1, put telescopes in space. That's the whole reason the Hubble Space Telescope exists. It floats above the atmosphere, so the stars stay perfectly steady. 2, adaptive optics. This is where ground-based telescopes use computers and mirrors that shift in real time to cancel out the atmosphere's turbulence. Basically, astronomers fight twinkle with high-tech anti-twinkle. And here's the fun fact. Sometimes planets do seem to twinkle a little, especially if the air is super turbulent or if they're low on the horizon. But compared to stars, the effect is tiny. If you're ever outside and you're not sure whether you're looking at a star or a planet, here's the simple test. If it's twinkling like crazy, it's a star. If it's shining steady like a flashlight, it's a planet. In fact, that's one of the easiest ways for casual stargazers to spot planets without a telescope. So the next time you're lying on the grass, staring up at the night sky, and you see that twinkle, remember, the stars themselves aren't flickering. They're burning steadily, light years away, blasting out energy without a care in the world. It's our wobbly atmosphere that's playing tricks on your eyes. Stars twinkle because Earth's air won't sit still. Planets don't twinkle because they're just a little too big in the sky to get pushed around the same way. And honestly, that makes twinkling even more magical. It's not just light from ancient suns. It's light that's been bent, twisted, and danced around by the very air you're breathing. You're not just seeing stars. You're seeing starlight that's been sculpted by Earth itself, one flicker at a time. Why we can't travel faster than light. All right, let's talk about one of the most famous limits in the universe, the speed of light. You've probably heard the phrase, "Nothing can go faster than light," a million times. It shows up in sci-fi movies, in physics documentaries, and even in random internet debates. But have you ever stopped and asked, why? Like, what's so special about light speed that it gets to be the ultimate cosmic speed limit? Why can't we just build a super rocket, hit the gas, and zoom past it? Here's the short answer. Because the universe is built in such a way that time and space themselves start to stretch and twist as you get close to light speed. And trying to go faster is like trying to sprint past the edge of reality itself. But don't worry. Let's slow this down and unpack it in a way that doesn't sound like a headache. First, some numbers. Light travels at about 300,000 kilometers per second. That's fast enough to go around the Earth more than 7 times in a single second. So right away, we're talking about speeds that are just mind-bending compared to anything we deal with in everyday life. The fastest rockets humans have ever launched are crawling turtles compared to this. Now here's the trick. Einstein's theory of relativity says that as you start moving faster and faster, weird stuff happens. It's not just your speed increasing. Space and time themselves start to behave differently. Imagine reality is like a stretchy fabric. The faster you push through it, the more it warps around you. For example, time slows down when you go really fast. This isn't just theory, it's been tested with atomic clocks on airplanes. The faster-moving clock literally ticks a little slower than the one sitting still. That's called time dilation. At everyday speeds, it's tiny and unnoticeable. But as you approach light speed, the effect gets massive. If you could somehow ride a spaceship at 99.999% the speed of light, you'd feel like only a few years passed on board, while decades or even centuries might pass back on Earth. Crazy, right? But that's not the only weirdness. Your mass also increases as you speed up. Think of mass like your resistance to acceleration. At rest, your mass is normal. As you go faster, it's like the universe is secretly adding invisible weights to you. Push harder, more weights get added. The closer you get to light speed, the heavier you become until eventually it would take infinite energy to push you to 100%. Infinite energy! And since we don't have infinite energy lying around, that's where the road ends. Another way to picture it, imagine you're running on a treadmill that speeds up every time you try to sprint. No matter how hard you run, the treadmill matches you and makes it harder.
Light speed is the point where the treadmill would need infinite electricity to keep going. You can get close, but you'll never actually hit it. So why does light itself get to break the rule? Well, because light isn't like you and me. Light particles, photons, don't have mass. They don't carry the baggage that slows things down. They just are energy. So they move at the maximum allowed speed of the universe right from the start. It's like they were born at the speed limit. Now, I know what you're probably thinking. What about warp drives or wormholes or all that sci-fi stuff where people just casually cruise faster than light? The truth is, physics doesn't completely rule out loopholes. Wormholes, for example, are like shortcuts through space-time. You wouldn't actually be going faster than light. You'd just be taking a shorter path. Warp drive ideas, like the famous Alcubierre drive, technically avoid breaking the light speed law too, because instead of moving faster than light, they squish space in front of the ship and stretch it behind. But all of these require forms of energy and physics we don't actually know how to make work yet. For now, they're just fascinating thought experiments. And here's one last mind-blowing thought. The speed of light isn't just about how fast stuff moves. It's also about how the universe communicates. Information, signals, cause and effect, all of it is limited by light speed. That's why if a star explodes 1,000 light years away, we won't see it for 1,000 years. The light is literally carrying the news to us across space at the only speed the universe allows. Faster than light would mean more than just faster travel. It would mean breaking causality, maybe even messing up the order of cause and effect. Imagine seeing something happen before its cause. That's the kind of paradox the universe refuses to allow. So next time you hear someone ask, "Why can't we just build something faster than light?" you'll know the answer. It's not about the engines or the rocket fuel. It's about the way reality itself is wired. Time slows, space bends, mass grows, and eventually you hit a wall that isn't physical. It's woven into the structure of the universe. Light speed isn't just a limit, it's the cosmic speedometer built into everything. And no matter how hard we try, for now, we're stuck in the slow lane, looking up at the stars and wondering what it would feel like to go faster than the universe itself allows.
How black holes suck things in. Black holes have this reputation as cosmic vacuum cleaners. The way movies show them, they're like giant space whirlpools, sucking up anything that wanders too close. Planets, stars, even light itself. You hear the word black hole and immediately think of some terrifying cosmic drain that just hoovers the universe into nothingness. But here's the thing. Black holes don't actually work like vacuums. They don't suck things in. What they really do is bend the very fabric of space and time so strongly that falling in becomes unavoidable. Let's slow it down. Imagine space not as emptiness, but as a giant, stretchy trampoline. Normally, planets and stars are like bowling balls sitting on the trampoline, making little dips. That dip is what we call gravity. It's the reason Earth holds on to the moon, or why you don't float away when you jump. The heavier the object, the deeper the dip. Now, take something with a ridiculous amount of mass, squeeze it down into a tiny area, and place that on the trampoline. The dip becomes so steep, so extreme, it turns into a bottomless well. That's basically a black hole, a place where the fabric of space itself has collapsed inward. So when you hear black holes suck things in, it's not suction like air rushing into a vacuum cleaner. It's that space is curved so dramatically that everything nearby has only one path, downward, toward the center. If you get too close, falling in isn't optional anymore. It's just the geometry of space telling you there's no other direction left. Here's a fun detail. If our sun magically turned into a black hole of the same mass, don't worry, it can't. Earth would keep orbiting just fine. We wouldn't get sucked in. We wouldn't be dragged across space. Why? Because the black hole would have the same gravity as the sun does now. Gravity depends on mass, not whether it's a star or a black hole. The real difference happens only if you wander too close, closer than the so-called event horizon. The event horizon is the ultimate point of no return. Cross it, and no matter how fast you try to escape, even if you move at the speed of light, you're stuck. Light itself can't climb out, which is why the hole looks black. To us on the outside, anything falling in just disappears, swallowed by darkness. But from the perspective of the object falling in, things get wild. Time itself slows down as you approach the horizon. To a distant observer, you look like you're frozen on the edge forever, fading into redder and redder light. To you, though, you just keep falling, faster and faster, until physics stops giving us answers. Scientists think the center of a black hole contains a singularity, a point where density becomes infinite and the laws of physics as we know them break down. But here's the honest truth. Nobody really knows what happens inside. Our best equations stop working at the singularity. It's like the universe saying, "Sorry, humans, that's classified." Now, let's clear up another misconception. Black holes don't go around gobbling everything in sight. They're not cosmic predators hunting down galaxies. In fact, you could orbit a black hole safely if you stayed far enough away. They only become scary if you drift too close. Think of them more like cliffs. You can walk around them just fine, but step too close to the edge and gravity takes over. And if you do fall in, the experience is the stuff of nightmares. Scientists call it spaghettification. And yes, that's the actual term. As you fall, the difference in gravity between your head and your feet gets so extreme that you'd be stretched into a long, thin noodle. It's not the most pleasant way to go, but hey, at least you'd be famous in physics textbooks. There's one more twist that makes black holes even stranger. They're not completely black. Thanks to quantum physics, black holes actually leak tiny amounts of energy, known as Hawking radiation. Over unimaginable timescales, this radiation means black holes can slowly evaporate. They're not eternal monsters. They're temporary, although temporary here means trillions upon trillions of years. So the next time someone says black holes are giant vacuums, you'll know better. They're not suction machines. They're regions where gravity has gone so extreme, space itself is tilted into a funnel with no way out.
They don't pull you in because they're hungry. They pull you in because the rules of geometry leave you no escape. And honestly, that makes them way cooler than the movie version. Because black holes aren't just dangerous, they're mysteries. They're places where our understanding of the universe hits its limit. And somewhere out there, millions of light years away, they're sitting quietly, bending space and time, waiting for curious minds like ours to keep asking questions.
Why the moon doesn't fall to Earth. Every time you look up at the night sky and see the moon hanging there, have you ever wondered, why doesn't it just fall down? I mean, gravity is real, right? The Earth is pulling on the moon with this huge gravitational force. So logically, shouldn't the moon just crash into us? Yet it doesn't. Instead, it's been hanging out there for billions of years, doing laps around our planet like some perfectly timed runner on a cosmic track. So what's going on? Why does the moon orbit instead of falling? To answer that, let's imagine something simpler. Picture yourself throwing a ball. If you toss it gently, it just arcs through the air and lands nearby. Throw it harder, it goes farther. If you somehow threw it insanely hard, like so hard that it matched the curve of the Earth, it would never hit the ground. Instead, it would keep falling toward Earth, but Earth's surface would curve away beneath it at the exact same rate. That's essentially what an orbit is, falling without ever landing. That's the moon's secret. The moon is falling toward Earth all the time. Gravity is pulling it inward, constantly tugging. But the moon also has this incredible sideways speed, about 3,600 kilometers per hour. That sideways motion means as it falls, it's always missing. It's like running around the edge of a cliff so perfectly that you never actually go over it. The combination of gravity pulling it down and motion carrying it forward creates a delicate balance. Here's a way to picture it. Imagine swinging a ball on a string around your head. The string is like Earth's gravity, always pulling the ball inward. The ball's forward motion keeps it moving in a circle instead of crashing into your hand. If you cut the string, the ball flies off in a straight line. That's exactly what would happen if Earth's gravity suddenly vanished. The moon would just zip away into space, drifting off forever. And this balance is incredibly precise. If the moon moved slower, gravity would win, and eventually it would spiral inward and collide with Earth. If it moved faster, its forward speed would overpower gravity, and it would escape into space. But right now, it's in the Goldilocks zone of orbital motion. Just the right speed, just the right pull. That's why it stays where it is. Here's another cool twist. This same balance keeps satellites in orbit around Earth. The International Space Station, for example, isn't floating in space because there's no gravity. It's actually falling toward Earth every second. But because it's moving so fast sideways, about 28,000 kilometers per hour, the Earth curves away beneath it. So the astronauts inside experience weightlessness, not because there's no gravity, but because they're in continuous free fall. Now, let's get back to the moon. It's not just sitting up there. It's slowly drifting away. Yep. Every year, the moon gets about 3.8 centimeters farther from Earth. That's roughly the speed your fingernails grow. This happens because of something called tidal interactions. The moon's gravity pulls on Earth's oceans, creating tides. But Earth's rotation drags those tides slightly ahead of the moon, and the gravitational tug from those bulges actually pushes the moon outward. Over millions of years, that adds up. So, in the very distant future, the moon will be much farther away, and Earth's day will be longer. This balance between gravity and motion isn't just some neat fact. It's why we exist. If the moon weren't in orbit, Earth's tides would be completely different. The planet's rotation might not be as stable, and life as we know it could be very, very different. The moon has been our constant companion, quietly stabilizing Earth for billions of years, making it a friendlier place for life. So, the next time someone says, "Why doesn't the moon just fall down?" you can tell them, actually, it is falling, but it's also moving forward so perfectly that it keeps missing. It's like the greatest cosmic balancing act ever, a graceful dance between gravity and speed. And that dance is what's kept the moon up there for longer than humans have even existed. Think about it. Every night you see it glowing above. You're not just looking at a rock in space. You're looking at an object performing a physics trick so precise, so perfect, that it's been working flawlessly for over 4 billion years. And it's still going strong. How seasons really work. Okay, let's clear up one of the biggest misconceptions people have about our planet. Why do we have seasons? A lot of people think it's because sometimes the Earth is closer to the sun and sometimes it's farther away. That sounds logical, right? Closer means hotter, farther means colder. The problem is, that's not how it works at all. In fact, Earth is actually closest to the sun in January, when it's winter in the northern hemisphere. So if distance were the reason, the seasons would be flipped. Clearly something else is going on. The real answer is one word: tilt. Earth isn't sitting upright as it spins through space. It's tilted on its axis by about 23.5 degrees. That small lean is the entire reason we have summer, winter, spring, and fall. Without that tilt, the planet would still spin, but every place would get about the same amount of sunlight year-round. No real seasons, just one long, endless climate pattern depending on where you lived. So how does tilt create seasons? Imagine holding a flashlight straight at a globe. If the globe is upright, the light hits evenly across the top and bottom. But tilt the globe, and suddenly one hemisphere is getting more direct light, while the other is getting weaker, spread out light. That's exactly what happens with Earth and the sun. When the northern hemisphere is tilted toward the sun, sunlight hits it more directly. The rays are concentrated, the days are longer, and that extra energy warms the land and oceans. That's summer in the north. At the same time, the southern hemisphere is tilted away from the sun, so it gets weaker sunlight, spread out over a bigger area, shorter days, colder temperatures, winter in the south. Then 6 months later, the situation flips. This is why seasons are opposite depending on where you live. When it's July and people in the US are sweating through summer, people in Australia are bundling up for winter. Same Earth, same sun, just opposite sides of the tilt. And here's something people often miss. It's not just about warmth, it's also about day length. In the summer, the sun doesn't just shine more directly, it also stays in the sky longer. Think about those long summer evenings when the sun sets at 9 p.m. That's hours of extra sunlight pouring energy into the ground. In the winter, the opposite happens.
the sun takes a shorter path across the sky, and it sets way earlier. So not only is the sunlight weaker, there's also less of it. Double whammy, colder temperatures. Want a fun example? Take the Arctic Circle. In the summer, places above it can get 24 hours of daylight. That's the midnight sun. But in the winter, they can go weeks or months without seeing the sun at all. That extreme swing is all because of Earth's tilt. Meanwhile, places near the equator barely notice seasons because the sunlight is always strong and direct. That's why countries near the equator are warm year-round, with just rainy and dry seasons instead of the dramatic summer-winter contrast. Now, you might be wondering, does Earth's distance from the sun play any role? Technically, yes, but it's tiny compared to tilt. The difference between Earth's closest point, perihelion, and farthest point, aphelion, is only about 5 million kilometers, which sounds huge, but compared to the total distance, about 150 million kilometers, it only changes the sunlight by about 7%. Not nearly enough to cause seasons. Tilt dominates the game. Another neat detail, Earth's tilt isn't perfectly steady. Over tens of thousands of years, it wobbles a little, sometimes more tilted, sometimes less. This axial wobble, combined with shifts in Earth's orbit, plays a role in long-term climate cycles like ice ages. So the tilt isn't just giving us summer BBQs and cozy winters by the fire. It's shaping the deep history of Earth's climate, too. And here's the kicker. If Earth weren't tilted, our planet would be unrecognizable. No snow-covered winters in the north, no blazing summers, no autumn leaves, no spring blooms. Human history, agriculture, even ancient civilizations, all of these are deeply tied to seasonal cycles. Tilt is the hidden puppeteer behind harvest festivals, winter holidays, and even migration patterns of animals. It basically runs the rhythm of life on Earth. So the next time you hear someone say, "It's summer because we're closer to the sun," you can smile and say, "Actually, we're tilted. That tiny 23.5-degree lean is why your summers are hot, your winters are cold, and why the planet feels alive with change instead of being stuck in eternal sameness." The tilt may be small, but its impact is enormous.
Why time moves slower near gravity. All right, here's a mind bender. Time itself doesn't tick at the same speed everywhere in the universe. That might sound like some sci-fi movie plot, but it's actually real physics. According to Einstein's theory of general relativity, gravity doesn't just pull on objects, it also stretches and bends space and time itself. Which means the stronger the gravity, the slower time passes. Let's start with a simple thought. Imagine you're standing near a giant mountain and your friend is far away on flat ground. Believe it or not, the clocks you both carry won't tick at the same speed. The one near the mountain, closer to a stronger gravitational field, will run just a tiny bit slower. Not by much. We're talking billions of a second difference, but it's there. And this has actually been proven with experiments. Scientists put super precise atomic clocks at different altitudes and found that clocks higher up, farther from Earth's gravity, run slightly faster than the ones closer to sea level. So why does this happen? The easiest way to think about it is that gravity isn't just a force pulling things down. Einstein showed us that gravity is the warping of space-time, the fabric that makes up the universe. When something massive, like Earth or the Sun, exists, it bends space-time around it. You can picture space-time like a stretched-out trampoline. Place a heavy ball in the middle, and the surface curves inward. Now, any smaller balls you roll near it will spiral inward. That's gravity. But here's the twist. Time itself is also part of that trampoline. When space-time curves, so does the flow of time. Closer to the mass, where the dent is deeper, time runs slower. Farther away, where space is less curved, time runs faster. That's why astronauts orbiting Earth on the International Space Station experience time a tiny bit differently than we do on the ground. It's also why GPS satellites need to constantly adjust their onboard clocks. They're farther from Earth's gravity, so their clocks tick a bit faster. If engineers didn't correct for that, your GPS directions would be completely wrong in just a day or two. Now, this effect becomes way more dramatic around extremely massive objects. Take a black hole, for example. The gravity near a black hole is so intense that time slows down massively. If you were hovering just outside the edge of a black hole, time for you would crawl compared to someone far away. From the perspective of an outside observer, it would look like you were frozen in time as you approached the black hole. For you, things would seem normal. You'd still feel time passing, but the rest of the universe would seem to speed up. That's how extreme gravity stretches time. This isn't just theory. It's been tested. One famous experiment was called the Hoeffel-Keating experiment in 1971. Scientists took atomic clocks on airplanes and flew them around the world, comparing them to clocks left on the ground. When the planes landed, the clocks showed tiny but measurable differences, exactly as Einstein's relativity predicted. So, yes, your location and the gravity around you literally affect how fast your time ticks. Here's a fun way to wrap your head around it. Imagine identical twins. One stays on Earth, the other spends years orbiting near a black hole, without falling in, of course. When the space-traveling twin comes back, they'd actually be younger than the twin who stayed home. Not because they ate healthier or used more sunscreen, but because time itself flowed differently for them. This is called the twin paradox. And while it sounds like a wild science fiction story, it's backed by real physics. And just to make it weirder, this isn't something humans feel. You don't notice your seconds stretching out because your body and your brain are slowed down at the same rate. Everything for you feels normal. It's only when you compare your clock with someone else's in a different gravitational field that the differences show up. So, the next time you hear someone say, "We all have the same 24 hours in a day," you can laugh a little. Technically, no, we don't. People on mountaintops, astronauts in orbit, and folks on Earth's surface all experience time at slightly different rates. Usually the differences are tiny, but in the grand scheme of the universe, gravity really does control the speed of time. Einstein's big insight was that space and time aren't separate. They're woven together as space-time. Bend one, and you bend the other. And that's why gravity doesn't just hold us down to the ground. It quietly messes with the very ticking of the universe itself.
How GPS knows your location so precisely. You probably pull out your phone, open Google Maps, and instantly it tells you exactly where you are. It's so normal now that we don't question it. But honestly, how on earth does a little phone in your pocket know whether you're standing on the left side of the street or the right side? That level of precision feels like magic. But it's not magic. It's a mix of physics, engineering, and a bit of Einstein's relativity thrown in.
First, GPS stands for Global Positioning System, and at its heart, it's basically a network of satellites flying high above Earth, about 20,000 kilometers up. There are at least 24 active satellites in orbit at any given time, spread out so that no matter where you are, your device can see several of them at once. Your phone is basically listening to these satellites, each one constantly broadcasting two important pieces of information: where it is in space and the exact time it sent the signal. Now, here's where triangulation comes in. Imagine you're lost, and you call three friends who are standing at known landmarks, one at a mall, one at a stadium, and one at a park. Each of them shouts, "You're 5 kilometers from me," or "You're 8 kilometers from me." By overlapping those circles of distance, you can figure out your exact position. That's exactly what GPS does. Your phone calculates how far you are from at least 4 satellites by measuring how long it took their signals to reach you. Since radio waves travel at the speed of light, even a billionth of a second matters. But here's the catch. Timing has to be ridiculously precise. If the clocks on satellites or your phone are even slightly off, your location would be way off too. Like, we're talking errors of several kilometers just from being a millionth of a second out of sync. That's why satellites don't use regular clocks. They use atomic clocks, which are insanely accurate. Your phone doesn't have one, that would be too expensive, but it doesn't need one. It just listens to signals from multiple satellites and adjusts for any tiny clock errors automatically. Now let's add the Einstein twist. Remember when we talked about relativity and how time runs differently depending on speed and gravity? Well, GPS satellites are affected by both. First, they're orbiting Earth at around 14,000 kilometers per hour, which makes their clocks run slightly slower due to special relativity. But at the same time, they're much farther from Earth's gravity than we are, so their clocks run slightly faster due to general relativity. Put those two effects together, and the difference comes out to about 38 microseconds per day. That might sound tiny, but if engineers didn't correct for that, GPS would drift off by about 10 kilometers every single day. Imagine your Maps app telling you to turn left straight into a lake. So yes, GPS literally wouldn't work without Einstein's theories of relativity. The system constantly corrects for those differences, making sure that the timing signals stay synced up perfectly. Now let's zoom back into your phone. Once it gets timing signals from 4 or more satellites, it can calculate your three-dimensional position: latitude, longitude, and altitude. That's how it knows whether you're in a car, in a skyscraper, or hiking a mountain trail. And modern systems go even further. They combine GPS with cell towers, Wi-Fi networks, and even motion sensors inside your phone to refine your location down to just a few meters or sometimes even centimeters. You've probably noticed how fast your GPS adjusts when you make a wrong turn. That's because your phone isn't just passively waiting. It's running algorithms that predict where you're going next, smoothing out any gaps when the satellite signals get blocked, like in tunnels or between tall buildings. And here's another wild thing. GPS isn't just for directions. Farmers use it for precision agriculture. Airplanes rely on it for navigation. Ships at sea use it to avoid accidents, and even financial systems like stock markets depend on GPS clocks to timestamp trades. Without GPS, huge parts of modern society would fall apart almost instantly. So the next time you open your Maps app and see that little blue dot following you around, remember, dozens of satellites are working together in space, bouncing signals across thousands of kilometers, applying Einstein's relativity corrections, and syncing clocks with unimaginable precision. All just to make sure you don't miss your turn at Starbucks. GPS isn't just some background technology. It's proof that mind-bending physics, high-tech engineering, and everyday life are all connected in ways we take for granted.
Why ice floats on water? Okay,
Here's one of those everyday mysteries we don't think twice about. Ice cubes floating in your drink. Seems obvious, right? But hold up. If you actually think about it, it's kinda weird. Most solids sink in their liquid form. Melted gold is denser than solid gold. Same for iron, same for lead. But water? Water's the rebel. Ice floats. And not only is it cool for your soda, it's actually one of the reasons life on Earth even exists. So, what's going on here? Why does water act so strange compared to almost every other liquid? Let's break it down in the simplest way possible. Water molecules are shaped like little bent V's, two hydrogen atoms stuck to an oxygen atom. They're tiny, but they're polar, meaning one side is slightly positive and the other is slightly negative. Think of them as microscopic magnets that like to stick together. In liquid water, these molecules are constantly jiggling around, sliding past each other, forming and breaking connections super quickly. That's what makes water flow. Now here comes the fun part. When water freezes, it doesn't just slow down and pack tighter like other liquids. Instead, the molecules arrange themselves into a very specific structure, thanks to something called hydrogen bonds. These bonds act like tiny arms stretching between molecules, holding them at a set distance. And here's the kicker. This structure forces the molecules farther apart than they were in liquid form. Imagine a bunch of people holding hands in a giant snowflake-shaped dance circle. They can't squeeze super close because their arms keep them spaced out. That's exactly what frozen water looks like on a molecular level. A big, open, hexagonal lattice that takes up more space than liquid water. The result? Ice is less dense than liquid water, and less density means it floats. That's why your ice cubes bob up to the top of your drink instead of sinking like little frozen rocks. Now, here's where it gets really interesting. This weird property of water literally makes life on Earth possible. Think about a lake in winter. If water behaved like other liquids, ice would sink to the bottom. The lake would fill up with solid ice, and eventually everything living in it would freeze to death. But since ice floats, it creates this insulating lid on top. The water underneath stays liquid, even in freezing weather, giving fish, plants, and other creatures a cozy environment to survive until spring. It's like nature's built-in life support system. And get this, scientists believe this quirk of water might even be connected to why Earth is such a perfect cradle for life. If ice didn't float, our ecosystems would be totally different, maybe even impossible. So the fact that water expands when it freezes isn't just some random accident. It's a fundamental rule that keeps everything alive. Want another neat side effect? Ice has this habit of expanding so forcefully that it can break apart solid rock. Have you seen cracks in the sidewalk that look like they got pried open? That's often because water seeped in, froze, and expanded. Over time, this process, called frost weathering, literally shapes mountains and landscapes. It's water being sneaky and using its strange property to carve the earth. Even in everyday life, you can see the same effect. Ever left a water bottle in the freezer overnight? The next morning it's swollen, maybe even cracked open. That's water's expansion in action. It refuses to be squeezed tighter once it locks into that ice lattice. So next time you drop ice cubes into your drink and watch them float to the top, remember, you're looking at one of nature's greatest cheats. Something that defies the usual rules of matter, keeps ecosystems alive, shapes landscapes, and makes human life possible. It's not just a party trick, it's survival science. Ice floats because water expands when it freezes. Weird, rare, and absolutely essential.
Without it, Earth wouldn't be the same world we know today.
Why your fingers wrinkle in water? All right, so picture this. You're chilling in the bathtub, or maybe washing dishes for way too long, and you notice your fingers and toes look like little raisins. They get all pruny, wrinkly, like you aged about 90 years in 20 minutes. Everyone's seen this, but here's the big question. Why does it happen? Why does our body do this weird little trick? Most people think it's because water soaks into your skin like a sponge, making it swell and wrinkle. That seems logical, right? But here's the twist. It's not actually what's happening. Scientists found out that your skin doesn't just passively absorb water and wrinkle up. Nope. It's way smarter than that. This is actually your nervous system in action. When you've been underwater for a while, your brain tells the blood vessels just beneath the skin in your fingers and toes to constrict, meaning they tighten up and pull back a little. That causes the skin on top to pucker and fold, creating those wrinkles. So this isn't just water messing with your skin. This is an active, controlled response from your body. And here's the really cool part. It's not just some random quirk. It's an adaptation with a purpose. Think about what happens when surfaces are wet. They get slippery. Wet rocks by a river, a bar of soap, even your bathroom floor. It's all harder to grip. Now, those little wrinkles on your fingers, they act like rain treads on a car tire. They channel water away, giving you better traction. With wrinkly fingers, you can hold on to slippery things more easily. Just like tires grip the road better in the rain because of their grooves. Scientists actually tested this. They had people pick up wet objects, some with smooth fingers and some with wrinkled ones. The wrinkled finger group won. Faster, stronger, and more secure grip. Evolutionarily, that would have been a huge survival advantage. Imagine our ancestors gathering food near rivers or streams. Being able to pick up wet fruit, grab fish, or climb on damp rocks without slipping could have meant the difference between eating or going hungry. Now, here's another fun twist. This effect only happens in your fingers and toes, not all over your body. Makes sense, right? Those are the parts we use for gripping and climbing. You don't need wrinkly elbows or wrinkly stomachs to hold on to stuff. So evolution didn't bother wasting energy on that. It's targeted engineering, like nature gave us built-in rain mode for our hands and feet. But wait, there's more! This wrinkling trick is so closely tied to your nervous system that doctors actually use it as a test for nerve damage. If someone's fingers don't wrinkle after soaking in water, it can mean there's an issue with the nerves in their hands. So yeah, your prune fingers aren't just a party trick. They're a window into how healthy your nervous system is. Let's not forget how it feels, too. Ever notice that when your fingers are wrinkly, they almost seem more sensitive? Like you're aware of every little ridge and texture. That's because the folds in the skin actually increase surface area, giving you more contact points with whatever you're holding. It's like your body is switching into high traction mode, not just physically, but also sensorily. And yet, there's still a bit of mystery. Scientists are pretty sure it's for grip, but the full evolutionary story isn't 100% locked in.
Some even suggest it could have helped with moving through wet vegetation or muddy terrain, kind of like natural off-road tires for your feet. Whatever the exact reason, one thing's clear. It's a built-in feature, not a flaw. So next time you're in the bath and your hands start looking ancient, don't think, ew, my skin's falling apart. Think, oh wow, my body just flipped on survival mode. You've basically unlocked a secret setting in your biology that goes all the way back to early humans trying not to drop a slippery fish dinner. Wrinkly fingers aren't water damage. They're a clever nervous system adaptation designed to help you hold on tight when the world gets wet and slippery. Nature thought ahead, and it gave us raisin hands for a reason. Why we see lightning before thunder. All right, let's set the scene. You're standing outside during a summer storm. The sky goes dark, the air feels heavy, and then, boom! A blinding flash of lightning cuts across the sky. But here's the thing, you see it instantly, and then you wait. A second passes, 2, maybe even 5. And then the thunder finally rolls in, shaking the ground under your feet. Every time this happens, people wonder, why do we see lightning first and then hear thunder later? Aren't they happening at the same time? Well, yes. Lightning and thunder are two parts of the same exact event. Lightning is basically a giant electrical spark ripping through the air, and thunder is the sound that spark makes as it tears the air apart. They happen together, like snapping your fingers. But the reason you see the flash before you hear the boom has nothing to do with timing. It's all about speed. Light and sound don't travel at the same pace. Light is insanely fast, like we're talking 300,000 kilometers per second fast. That's about 186,000 miles per second. To put that in perspective, light could circle the Earth more than 7 times in just 1 second. It's basically instant as far as our human senses are concerned. Now compare that with sound. Sound is slow. Don't get me wrong, it's not crawling. It travels at about 343 meters per second in normal air. That's about 1,125 feet per second. That's still quick enough to reach you almost immediately in day-to-day life. But compared to light, sound is like a bicycle trying to raise a rocket ship. It doesn't stand a chance. So when lightning strikes, the flash of light rockets straight to your eyes almost instantly. Meanwhile, the sound of thunder is still making its way through the air, vibrating molecules one by one until it finally reaches your ears. That's why there's that weird pause. And here's a fun trick. You can actually use that delay to figure out how far away the lightning strike was. It's called the flash to bang method. Every 5 seconds between the flash and the boom equals about 1 mile of distance. So if you count 10 seconds, that lightning bolt hit about 2 miles away. Pretty handy when you're trying to decide whether it's time to head inside or if you're still safe to watch the show. But let's go deeper for a second. Why does thunder even exist? Lightning isn't just bright, it's hot. In fact, a single bolt of lightning can heat the air around it to about 30,000 kelvins. That's 5 times hotter than the surface of the sun. Imagine what that does to the air. It's like instantly turning a column of air into an explosive expansion chamber. The air around the lightning bolt expands so violently and so fast that it creates a shockwave, a super loud boom we call thunder. And that boom isn't always just a sharp crack. Sometimes it rumbles and rolls for several seconds. That's because lightning isn't usually just one short bolt. It can zigzag for miles through the sky. Every part of that jagged path creates its own little burst of sound. And as those different sound waves reach you at slightly different times, they blend into that long, low rumble.
That's why some thunder sounds sharp and close, and others sound like a drum, rolling far in the distance. Another cool detail, the delay between lightning and thunder also helps explain why storms can be so misleading. You might see the lightning and think, "Whoa, that's close," but then you don't hear thunder for 10 seconds, and suddenly you realize the strike was miles away. On the flip side, if you see the flash and the thunder follows almost instantly, you know that storm is right on top of you, which is when you should probably get to safety. And speaking of safety, lightning is way more dangerous than people give it credit for. Because we see it first, we sometimes underestimate how close it is. But remember, if you can see the flash, you're within striking distance. Lightning can travel outward for miles, even from a cloud you don't think is nearby. So as beautiful as it is, lightning is not just a light show. It's nature's most powerful electrical system at work. So the reason we see lightning before we hear thunder isn't magic. It's just physics. Light is so fast that our brains get the message almost instantly, while sound plods along, taking its sweet time. It's a reminder that even though both light and sound reach us eventually, the universe has a clear favorite when it comes to speed. Next time you're out watching a storm, try counting the seconds. You'll feel like you've got a superpower, predicting how far away the storm is just by paying attention to the gap between light and sound. And remember, the flash and the boom are two sides of the same coin. They're just taking different roads to get to you. Lightning speaks in light, thunder speaks in sound, and your brain stitches the story together.
Why soap actually cleans? Let's be honest, soap is so ordinary we barely think about it. You use it every day, right? You wash your hands, your dishes, your clothes, your car. But here's the weird thing. Most of us don't really know why soap works. Like, why does this slimy bar or squirt of liquid actually make things clean? It's not like it's scrubbing for you. It's just a chemical. So what's going on? To understand this, let's start with the problem. Imagine you get some grease on your hands after fixing your bike or cooking bacon. You go to the sink, run your hands under water, and nothing happens. The grease just sits there laughing at you. Why? Because water and oil don't mix. They're like that pair of relatives who can't stand each other at family gatherings. No matter how much water you pour in oil, it just beads up and slides around. That's because water is made of polar molecules. It's got a positive side and a negative side, like tiny magnets. They love sticking together, and they don't want to mess with oil molecules, which are nonpolar. Oil's like, nah, I'll just hang out with my own kind. So water alone is pretty useless against greasy dirt. Enter soap, the secret agent in this story. Soap molecules are special because they're basically double agents. One end of a soap molecule is hydrophilic. That's a fancy way of saying water-loving. It's polar, so it's perfectly happy to mingle with water molecules. The other end, though, is hydrophobic, meaning water-fearing. But here's the catch. That end actually loves oil and grease. So every soap molecule is like a tiny two-faced diplomat, one hand shaking water's hand, the other grabbing onto oil. When you lather up with soap, millions of these molecules swarm the dirt and grease. The hydrophobic tails bury themselves into the oil like little anchors, while the hydrophilic heads stick out into the water. The result is a microscopic structure called a micelle. Picture a bunch of soap molecules forming a bubble around a drop of grease. The oily gunk is trapped inside, safely surrounded by a shield of soak. And since the outside of that bubble is water-friendly, the whole thing can be rinsed away easily.
The grease that wouldn't budge before suddenly just slides right off with the rinse water. Boom, clean hands. That's the magic of soap. It doesn't destroy the dirt. It just traps it in a way water can carry it away. It's like giving oil a disguise so it can sneak out with the water without anyone noticing. Now, here's where it gets even cooler. Soap doesn't just deal with oil and dirt, it can also take down germs. Many bacteria and viruses, including the one that caused COVID-19, have a fatty outer layer called a lipid membrane. Guess what soap molecules love to do? Yep, those hydrophobic tails latch on to that fatty layer and rip it apart. It's like soap molecules stabbing little holes in a balloon until it bursts. That's why washing your hands with plain old soap and water is often more effective than fancy hand sanitizers. It literally destroys the germ's protective coat. And think about how universal this is. Whether it's laundry detergent, breaking up sweat and skin oils in your clothes, dish soap tackling cooking grease on your pans, or shampoo grabbing onto the natural oils in your hair, soap's double-ended trick is doing all the heavy lifting. It's like a tiny army of molecular janitors scrubbing everything clean at a level we can't even see. There's also a reason why soap foams. You've probably noticed the bubbles, right? While the foam itself doesn't really clean much, it's a side effect of soap molecules trapping little pockets of air. But bubbles are actually useful to us because they help spread the soap around evenly, making sure it covers more surface area. It's like a built-in signal that the soap is working its way everywhere. Here's something that might surprise you. Humans have been using versions of soap for thousands of years. Ancient Babylonians were making soap-like substances as far back as 2800 BCE, mixing fats with ash. They probably didn't know about micelles or hydrophilic ends, but they knew it worked. And we've just refined the recipe since then, making it gentler, scented, and way more effective. So next time you wash your hands and feel that slippery, squeaky clean effect, remember what's happening on a microscopic level. Tiny soap molecules are locking onto grease, wrapping it up, and escorting it straight down the drain. At the same time, they might be ripping apart harmful germs you can't even see. It's not just soap. It's one of the simplest, most powerful bits of chemistry you use every single day without realizing it. Pretty wild, right? Why onions make you cry? Okay, let's be honest. Cutting onions feels like emotional blackmail. You're just trying to make dinner, and suddenly you look like you've been dumped in the middle of chopping vegetables. Tears streaming down your face, nose running, everyone in the kitchen asking if you're okay. But here's the thing. Onions aren't trying to hurt your feelings. They're just doing chemistry. So let's break down why onions have this weird power to turn even the toughest person into a teary mess. First, onions are plants, and plants can't exactly run away from danger. Their only defense is chemistry. When an animal, insect, or even a human slices into them, the onion has built-in booby traps to make the attacker think twice. Inside an onion's cells are different chemical compartments. When the onion is whole, those compartments keep everything separate, nice and safe. But when you cut into it, you break those cells open and the chemicals inside mix together, kind of like two puzzle pieces finally snapping into place. The main culprit here is sulfur. Onions, like other members of the allium family, garlic, leeks, shallots,
soak up sulfur from the soil as they grow. That sulfur ends up stored in special molecules inside the onion. When you slice into it, an enzyme called alliinase is released. It immediately reacts with those sulfur molecules, producing a new set of chemicals, including something called syn-propanethyl S-oxide. That's the real villain in this crying story. Syn-propanethyl S-oxide is what scientists call a lacrimatory agent, literally tear-inducing. It's a gas, so as soon as it forms, it floats upward into the air and drifts toward your face. The second it reaches your eyes, it reacts with the water in them. And what happens when sulfur compounds meet water? They form a weak version of sulfuric acid. Now, don't panic. It's not strong enough to burn you like the acid in a chemistry lab, but it's irritating enough to set off your eye's emergency system. Your eyes are incredibly sensitive to protect themselves. They have nerves constantly checking for dust, smoke, chemicals, anything that could damage them. The moment those nerves detect the tiny bit of acid from the onion gas, they send a signal. Danger! Flush this out! That's when your tear glands go into overdrive, pumping out water to wash away the irritant. You start crying, not because you're sad, but because your body is basically treating you like you just walked through a cloud of pepper spray. Now, some of you might be thinking, okay, but why doesn't this happen with every vegetable I chop? Good question. It comes down to evolution. Onions developed this chemical defense as a survival strategy. If some animal takes a bite and their eyes start stinging, they're less likely to eat the rest of the plant. Over thousands of years, onions that made stronger tear-inducing chemicals had a better chance of surviving. So, ironically, the fact that we cry when chopping onions is proof that their strategy worked pretty well. Of course, humans being humans, we've come up with tricks to fight back. Some people chill onions in the fridge before chopping. Why? Because cooler temperatures slow down the enzyme reaction that makes the tear gas. Others chop onions under running water or near a fan. This helps carry the gas away before it reaches your eyes. You can even buy tearless onions, which are specially bred to produce less of that syn-propanethyl S-oxide compound. They don't taste quite as sharp, but hey, they won't make you bawl your eyes out halfway through making stir-fry. Here's something fun. Your nose actually gets in on the action too. Ever notice your nose runs when you chop onions? That's the same sulfur compounds irritating the sensitive lining in your nasal passages. Your body's reaction is to produce mucus to trap and flush them out, which is why you end up sniffling like you just watched a sad movie marathon. But here's the kicker. This tear-inducing side effect is also why onions taste so good when cooked. The same sulfur compounds that make your eyes sting are responsible for that deep, savory, almost meaty flavor onions add to food. When you sauté or roast them, the heat breaks those chemicals down into sweeter, caramelized flavors. So, the very thing that makes onions annoying to chop is what makes them magical in the pan. It's a package deal. Pain up front, delicious payoff later. So next time you're chopping onions and tears start rolling down your face, don't think of it as your body betraying you. Think of it as you unlocking the onion's secret defense system. Your tears are proof that you just triggered a little chemical war, and you came out the winner because in the end, you're still going to eat the onion. Pretty cool, right? A humble kitchen staple secretly carrying a built-in tear gas grenade, and all it takes is a knife to set it off. And the best part, even though it makes you cry, it's one of the main reasons your food tastes amazing.
how caffeine keeps you awake. Okay, let's talk about everyone's favorite legal drug, caffeine. Seriously, it's the most widely used psychoactive substance on the planet. Whether it's coffee, tea, energy drinks, or even chocolate, most of us rely on it to kickstart the day or survive that mid-afternoon slump. But have you ever wondered what's actually going on in your brain when caffeine magically turns zombie you into functional you? Spoiler, it's not giving you extra energy. It's more like it's tricking your brain into ignoring the signals that tell you to rest. Here's how it works. Inside your brain, there's a chemical called adenosine. Think of adenosine as your brain's built-in sleep pressure meter. Every time your neurons fire while you're awake, they release energy and burn fuel. As a byproduct, adenosine slowly builds up in your brain throughout the day. The more adenosine you've got floating around, the sleepier you feel. It's basically your brain saying, hey, you've been up a while. Maybe chill and take a nap. Now, adenosine works by binding to special docking stations on your brain cells called adenosine receptors. When it docks, it sends the signal, slow down, relax, get ready for sleep. By nighttime, you're usually got a lot of adenosine hanging out, which is why your eyelids feel heavy and your bed suddenly looks like the most inviting thing in the world. Enter caffeine. Caffeine's molecule is shaped suspiciously like adenosine. So when you drink coffee, caffeine sneaks into those docking stations and basically sits there like an imposter. The key difference, unlike adenosine, caffeine doesn't activate the slow down signal. It just blocks the spot, so the real adenosine can't get in. Imagine adenosine walking up to its parking space only to find some flashy sports car already parked there. No space left, no signal sent. That's what keeps you from feeling tired. But here's the catch. Caffeine doesn't actually give you energy. What it does is stop your brain from noticing how tired it is. Your neurons keep firing away at their usual pace, and other brain chemicals like dopamine and norepinephrine start increasing. Those chemicals boost alertness, mood, and even reaction time. That's why your first sip of coffee in the morning feels like flipping a wake-up switch. Of course, your body isn't dumb. If you drink caffeine regularly, your brain adapts. It starts growing more adenosine receptors to make up for the blocked ones. That's why, over time, 1 cup of coffee might not do the trick anymore. You need 2 or maybe 3 just to feel normal. And if you suddenly quit, all those extra receptors are wide open for adenosine to rush in, making you feel more tired than ever. That's caffeine withdrawal. Headaches, fatigue, crankiness, the whole package. Here's another fun fact. Caffeine doesn't stay in your system forever. Your liver eventually breaks it down with enzymes, and how fast that happens depends on your genetics. Some people metabolize caffeine super quickly. They can drink an espresso at 9 p.m. and sleep like a baby. Others process it slowly, so even a morning coffee can leave them tossing and turning at night. That's why caffeine affects everyone a little differently. And get this, caffeine's half-life, the time it takes for half of it to clear out of your body, is about 5 to 6 hours on average. So that innocent 4 p.m. latte, half of it might still be buzzing around in your brain at 10 p.m., blocking adenosine and keeping you awake. If you're sensitive, that's basically a one-way ticket to insomnia city. Now, beyond just wakefulness, caffeine can actually improve certain types of performance. Studies show it helps with focus, memory, reaction time, and even physical endurance. Athletes sometimes use caffeine to push harder in training or competition because it reduces how much effort their muscles feel like they're exerting. You're not suddenly stronger, it just convinces your brain that the workout isn't as hard. But, like with anything, there's a balance. Too much caffeine and you're jittery, anxious, maybe even nauseated. That's because it also stimulates your nervous system and boosts adrenaline, your body's fight or flight hormone. Great in small doses for focus, not so great when your hands start shaking and your heart feels like it's doing backflips. So let's recap. Caffeine works by playing a sneaky little trick on your brain. Instead of giving you actual fuel, it blocks adenosine from docking, which delays the tired signals. Your brain feels more alert, your mood perks up, and suddenly you're ready to tackle work, school, or whatever's on your plate. But underneath that illusion, your body is still building up sleep pressure. Eventually, when the caffeine wears off, you crash and all that adenosine finally gets its turn. That's why sometimes after a long caffeine-fueled day, you feel like you're melting into your bed. So next time you sip your coffee, just remember, it's less of an energy boost and more of a clever disguise. Your brain isn't wide awake, it's just being tricked into thinking it's not tired. And honestly, for millions of people every morning, that little trick is nothing short of magic.
Why cutting bread is harder than it looks. All right, let's be honest. Cutting bread should be one of the simplest tasks in the kitchen, right? It's just bread. But if you've ever tried slicing into a fresh loaf, you know it can feel like a full-on battle. The crust is either so tough your knife skids off like it's armored, or the inside is so soft it just squishes down into a sad pancake instead of giving you those nice, clean slices you see in bakery ads. But here's the thing. It's not that you're clumsy. Bread is secretly a lot more complicated than it looks, and the big culprit here is something called gluten. So, let's back up a little. What is gluten? It's a protein found in wheat flour, and it's the backbone of basically every bread you've ever eaten. When you mix flour with water, the proteins in gluten, mainly glutenin and gliadin, link up and form a stretchy, elastic network. Imagine a net made of microscopic rubber bands. That's gluten. And when you knead bread dough, you're strengthening that net, making it stretchy enough to trap bubbles of gas from yeast. That's what makes bread rise and gives it that airy, chewy structure. Now here's where your knife comes in. That gluten network is strong, like surprisingly strong. It's designed to hold the whole loaf together through baking, expanding, and crust formation. Once the bread is baked, the inside has this spongy, elastic texture, while the crust hardens into a shield. So when you try to cut through it, your knife is actually fighting two very different enemies, the tough outer crust and the stretchy, springy interior. Think about it like this. Have you ever tried cutting a bouncy ball with a dull knife? Instead of slicing, the ball just squashes and slips away. That's what happens with fresh bread. The gluten network inside resists the pressure of your knife, so instead of cutting neatly, you just end up compressing the loaf. This is why your slice sometimes looks more like a mangled wedge than anything else. This is also why bakeries and chefs swear by serrated knives for bread. Those jagged saw-like edges don't just press down, They grip and tear through the crust, then see their way cleanly through the elastic gluten inside. If you've ever tried cutting bread with a regular smooth kitchen knife, you've probably ended up with crumbs everywhere and slices that look like they lost a bar fight. That's because smooth blades push, while serrated blades saw. But here's a fun twist. The temperature of the bread makes a huge difference. Fresh out of the oven, bread is basically impossible to cut cleanly. The steam inside is still keeping the crumbs soft and squishy, and the gluten network is at peak elasticity. That's why bakers usually recommend letting bread cool at least an hour before slicing. Once it cools, the interior firms up a bit, and suddenly your knife has a fighting chance. There's also the flour factor. Breads made with higher protein flour, like bread flour, have more gluten, which means more chewiness and elasticity. That makes them harder to slice than something like a soft brioche or cake, which uses lower protein flour and has a weaker gluten structure. That's why sandwich bread from the store slices so neatly. It's engineered to be soft and consistent with less gluten toughness. Compare that to a rustic sourdough loaf, and suddenly you're hacking away like you're carving a tree trunk. Here's another little secret. Bakers sometimes cheat with scoring. Those decorative slashes you see on artisan bread, they're not just for looks. By slashing the dough before baking, you're giving the bread pre-made weak points. This helps control how the crust cracks and helps the bread expand in a way that makes slicing later just a bit easier. Without scoring, the crust might explode into random jagged spots, making your slicing nightmare even worse. And don't even get me started on bread knives that aren't sharp. A dull serrated knife is basically useless. It'll just shred your bread into a pile of crumbs. A sharp bread knife, though, that's like a hot knife through butter. Well, almost. So let's put it all together. Cutting bread is tough because you're up against two forces at once: the hard, brittle crust and the springy, elastic gluten network inside. Your knife has to both break through armor and deal with rubber band resistance, all while not squishing the whole thing flat. Serrated knives, cooled bread, and lower gluten loaves make the process easier. But at the end of the day, if your slices aren't perfect, don't blame yourself. Blame the science. And maybe next time you tear into a loaf and wonder why it's putting up so much of a fight, just remember that resistance you feel is literally the structure that made the bread possible. The gluten is doing its job just a little too well.
Why spicy food feels hot? All right, let me ask you something. Have you ever eaten something so spicy that you felt like smoke should be coming out of your ears? You're sweating, your tongue feels like it's on fire, and suddenly you're questioning all of your life choices? But here's the funny part. That heat you're feeling isn't real heat at all. The food isn't literally raising the temperature inside your mouth. What's happening is way sneakier. It's a chemical trick being played directly on your nervous system. The main culprit is a compound called capsaicin. It's the active ingredient in chili peppers that makes them spicy. But capsaicin isn't actually hot like boiling water or fire. It's just a molecule that messes with the way your brain interprets pain and temperature. Think of it as a prankster chemical that flips the wrong switches in your body. Here's how it works. Your tongue, mouth, and throat are covered in nerve endings, and some of those nerves are designed to detect temperature and pain. They have receptors called TRPV1 receptors. Don't worry, you don't need to remember the name. Normally, these receptors light up when you put something genuinely hot in your mouth, like soup that just came off the stove or coffee that's way too fresh. When the receptors get triggered, they send a signal to your brain that says, "Hey, this is hot, be careful." That's your body's natural warning system against burning yourself. Capsaicin, however, sneaks in and activates those same receptors, even though there's no actual heat involved. It's like it picks the lock and fools your brain into thinking your mouth is on fire.
That's why spicy food doesn't just taste different, it actually feels hot, because your brain is convinced it is. Now, here's the interesting part. Your body reacts to that fake heat the same way it reacts to real heat. You start sweating to cool yourself down, your heart rate might go up, and sometimes your nose runs or your eyes water. That's not just coincidence. That's your body activating its natural cooling systems against what it thinks is genuine burning. And then there's the infamous burning aftershock. Capsaicin sticks to your tongue and mouth, and because it's oil-based, it doesn't wash away with water. That's why chugging a glass of water when you eat something super spicy never works. It just spreads the capsaicin around like hot sauce on a paintbrush. If you really want relief, you need something fatty or dairy-based, like milk or yogurt. The fat molecules help dissolve the capsaicin and carry it away from your nerve receptors, which is why chefs always tell you that milk is the ultimate antidote for spicy food. What's even crazier is that your body can get used to capsaicin. If you eat spicy food regularly, your nerve receptors start to dull their response. In other words, your brain stops freaking out as much, and you build up a tolerance. That's why people who grow up eating chili peppers every day can munch on something that makes everyone else cry and they barely break a sweat. It's not that they don't feel it, it's that their nervous system has learned to chill out. Here is a cool side fact. Capsaicin is so good at tricking your pain receptors that scientists actually use it in medicine. There are capsaicin creams and patches that help relieve chronic pain. Sounds backwards, right? But here's the trick. If you expose those pain receptors to capsaicin for long enough, they eventually get desensitized and stop sending pain signals. So, weirdly enough, the same thing that makes your tongue feel like it's melting can also help people with arthritis or nerve pain feel less discomfort. Now, you might be wondering, why did chili peppers even evolve this chemical in the first place? It wasn't to torture humans, I promise. Capsaicin is actually a defense mechanism. Plants can't run away from predators, so they use chemistry to protect themselves. Capsaicin specifically targets mammals, like us, because mammals chew seeds, destroying the plant's chance to reproduce. But birds don't have the same receptors we do, so they don't feel the burn at all. They can eat chili peppers without any problem, swallow the seeds whole, and then carry those seeds far away before dropping them in new soil. It's a perfect win-win for the plant. Mammals stay away, but birds help spread its babies. And let's be real here. Spicy food is kind of an odd human obsession. We're basically the only species that willingly seeks out food that feels painful. I mean, you don't see squirrels challenging each other to eat ghost peppers, but for us, there's almost a thrill to it. Some scientists call it benign masochism, that weird human tendency to enjoy experiences that feel bad in the moment, but we know they're not actually harmful. It's the same reason people like roller coasters or horror movies. Spicy food is just another way we get that rush. So the next time you're sitting there with your mouth on fire after eating hot wings, just remember, you're not actually burning. You've just been outsmarted by a little molecule called capsaicin that convinced your brain you were in danger. It's not heat, it's a trick. And somehow, for reasons that probably say a lot about human nature, most of us keep going back for more.
Why ice cream can give you brain freeze. Okay, picture this. You're outside on a hot day, the sun's beating down, and you've got this massive cone of ice cream. You take a big bite because, honestly, who actually nibbles ice cream like a civilized person? And then, boom, it feels like someone just swung an ice pick right between your eyes. That's brain freeze. It's one of those things that hits out of nowhere, feels way too dramatic for what just happened, and then disappears almost as quickly as it came. But what's going on here? Why does something as innocent as ice cream suddenly feel like a weapon aimed at your forehead? So here's the deal.
Brain freeze isn't actually happening in your brain. Nothing is literally freezing inside your skull, thank goodness. What's really happening is all about your palate. That's the roof of your mouth. When you slam super cold stuff like ice cream or a frozen drink against that area, the sudden drop in temperature messes with the blood vessels there. Normally, the blood vessels in your palate are pretty chill, pun intended. But when cold hits, they do this quick dance. They constrict, get smaller to protect against the cold, and then they dilate again to bring warmth back. It's like they freak out for a second and overcompensate. That rapid expansion and contraction sets off nerve signals. And here's where the plot twist comes in. Those nerves don't just stay local in your mouth. They send signals through the trigeminal nerve, one of the major nerves in your face. Now, the trigeminal nerve is a bit of a drama queen. It's connected not only to your mouth, but also to your forehead and eyes. So when it gets activated by that sudden cold, your brain kind of misinterprets the message. Instead of saying, hey, the roof of your mouth is cold, it goes, emergency, pain in the forehead. And that's why you feel that sharp stabbing sensation right behind your eyes or in your temples. The technical term for this mix-up is referred pain, when your body feels pain in one spot, even though the real problem is somewhere else. And here's another fun twist. Brain freeze happens really fast. We're talking just a few seconds after the cold touches your palate. That's why it feels like such a sneak attack. But luckily, it also goes away quickly, usually within 20 to 30 seconds. That's because once the blood vessels settle down, the nerves stop freaking out, and your brain realizes, oh, wait, we're fine. Now, let's get to the part everyone really wants to know. How do you stop brain freeze once it hits? Because let's be honest, when you're clutching your forehead in public, you do almost anything for relief. The trick is to warm up the roof of your mouth again. Some people press their tongue against it. Others take a sip of warm water, and I've even seen folks press their thumb against the roof of their mouth like they're hitting a reset button. The idea is the same. Get those blood vessels to chill out. Well, unchill out in this case. Here's something you might not know. Scientists actually study brain freeze as a way to understand migraines. Yeah, those brutal headaches that can last hours or days. Migraines and brain freeze both seem to involve sudden changes in blood vessels and nerve signals in the head. So by studying that short burst of ice cream-induced pain, researchers hope to better understand how to prevent or treat chronic headaches. Kind of funny, right? Something as silly as a snow cone could be giving us clues about serious medical problems. And before you start thinking brain freeze is some kind of modern problem caused by giant Slurpees or milkshakes, nope, it's been around as long as humans have been eating cold things. We just never really thought about it much until we started gulping down frozen treats in huge quantities. Our ancestors probably got it too, though maybe from drinking super cold river water or chewing on ice or snow. Now, here's the part that always cracks me up. Despite knowing full well that brain freeze hurts, people rarely stop eating ice cream because of it. We'll pause, grimace, maybe hold our forehead dramatically, and then keep eating. Because apparently the risk of temporary skull pain is worth the joy of frozen sugar. That right there is peak human behavior. So the next time you're hanging out with friends and someone gets brain freeze, you can tell them, actually, nothing's freezing in your brain. It's just the blood vessels in your mouth throwing a tantrum and your nerves overreacting. You'll sound smart, and you'll also get to keep enjoying your ice cream like the brave soldier you are. In the end, brain freeze is kind of like nature's reminder not to rush through the good stuff. Slow down, savor your ice cream, and you won't get stabbed in the head by your own nervous system. But let's be real, you're probably still going to take that giant first bite anyway.
Why microwaves heat food unevenly? Okay, let me paint a scene. You've got leftovers from last night, maybe pizza, maybe that suspicious-looking Chinese takeout box in the fridge. You're starving, so you toss it in the microwave, punch in a random time, because nobody actually calculates that, and wait. Ding!
You pull it out, take a bite, and instantly regret it. The crust is lava hot, but the cheese is still cold. Or worse, part of it is frozen solid. That weird mix of scalding and icy. Welcome to the mysterious world of uneven microwave heating. So why does this happen? Isn't a microwave supposed to, heat food? Shouldn't it all heat at the same time? Well, the truth is, microwaves are both genius and flawed. And the reason they're flawed is because of something called standing waves. Don't worry, I'm not going to throw a physics textbook at you. We'll keep this simple. Inside your microwave, there's this little machine part called a magnetron. It's basically the heart of the whole operation. The magnetron shoots out invisible waves, actual microwaves, that bounce around inside the metal box of your microwave oven. These waves carry energy, and when they hit the water molecules in your food, those molecules start vibrating like crazy. That vibration is what we feel as heat. Sounds simple enough, right? Here's where it gets tricky. Those microwaves don't just zoom around randomly. They bounce back and forth between the walls of the oven. And when waves bounce, they can overlap with each other. Sometimes, when two waves overlap, they add up to become stronger. That's called a hot spot. Other times, they cancel each other out and create a cold spot. Put all those hot spots and cold spots together, and you get what we call a standing wave pattern. Now imagine your plate of food sitting in the middle of all this. Parts of your food end up in the hot spots, where they're blasted with energy and heat up super fast. But the unlucky parts that are sitting in cold spots, they barely get any energy. So they stay cold, and boom. That's why your pizza slice is both boiling and chilly in the same bite. This is also why your microwave has a turntable. Ever wonder why the plate spins around in there? That's not just to make your meal look like it's on display. It's actually to move your food through those hot and cold spots. Instead of sitting in one place and getting cooked unevenly, your food slowly rotates so different parts pass through different areas of the standing wave pattern. It's not perfect, but it's way better than just leaving your food in one place. Some fancy microwaves even have a little mode stir fan in the top that bounces the waves around more chaotically so you don't end up with such sharp hot and cold zones. Now, here's something cool you probably didn't know. You can actually see standing waves inside your microwave. There's a little science experiment where you cover a plate with mini marshmallows, heat them up without the turntable spinning, and watch where they melt first. You'll notice some marshmallows puff up and turn gooey, while others stay pretty much intact. The melted ones are sitting in hot spots, and the untouched ones are in cold spots. Congratulations, you just mapped the standing wave pattern of your microwave. Another fun fact, this uneven heating is also why most microwave instructions tell you to stir halfway through cooking. Like when you heat up soup or oatmeal, the box always says microwave for 2 minutes, stir, and then microwave again. That's not some cruel joke to make you wait longer. It's actually to move the cold spots and hot spots around in your food so the heat spreads out more evenly. Without stirring, you might burn your tongue on boiling broth while still crunching through half-frozen carrots. So the uneven heating isn't because your microwave is broken. It's just how microwaves work. They're efficient, they're fast, but they're not exactly precision tools. And that's why a slice of lasagna comes out with the edges blistering hot while the middle is still ice cold. The middle might have been sitting in a dead zone or the waves canceled each other out. And if you're wondering why microwaves don't just fix this with better design, well, they've tried. Some microwaves have multiple magnetrons firing from different directions. Others have stirrers or bouncing panels to scatter wave more evenly. But at the end of the day, it's still a battle against physics. So the next time you're annoyed that your Hot Pocket is half molten lava and half frozen core, just remember it's not the microwave being lazy. It's those standing waves, creating a battlefield of hot and cold zones right inside the box. And honestly, this makes me feel a little bit better about it. At least now when you're blowing on your tongue after a painful first bite, you can say, ah yes, the noble standing waves strike again.
Why you get goosebumps. All right, picture this. You're watching a scary movie, and right when the monster jumps out, you feel your skin prickle.
Or maybe you step outside on a chilly morning, and suddenly your arms look like they've grown tiny bumps all over. Yup, goosebumps. Weird little dots that show up on your skin without asking permission. But have you ever wondered why your body does that? Like, what's the point of turning your skin into a plucked chicken look-alike? Here's the funny thing. Goosebumps actually made a lot more sense millions of years ago, just not so much today. They're what scientists call a vestigial reflex, something we inherited from our ancestors that doesn't really serve its original purpose anymore. Kind of like wisdom teeth, or the appendix, or that friend who insists on bringing a guitar to every party. So what's the deal? Let's go way back in time. Imagine early humans, but even before that, think about our mammal ancestors. Creatures covered in thick fur. When they felt cold, tiny muscles at the base of each hair would contract, making the hair stand straight up. This did two things. It trapped more air between the hairs, creating an insulating layer that kept them warmer, and it made them look bigger and more intimidating if they were scared or threatened. You've probably seen a cat puff up its fur when it's startled, right? Tail gets bushy, back arches, the whole Halloween cat pose. That's the exact same reflex, except it actually works for a cat. It makes them look like a much bigger, more scary animal. For humans, not so much. The only thing that happens to us is our arm hair sticks up a little, and let's be real, nobody is running away because you suddenly look slightly furrier. Fast forward to now. Humans lost most of that thick body hair over the course of evolution, but we kept the reflex. So when it's cold, or when you're scared, or even when you feel strong emotions like listening to a powerful piece of music, your body still pulls the same trick. Little muscles, called erector pili, tug at the base of your hair follicles, your hair is stand up, and boom, goosebumps. And why goosebumps? Well, if you've ever seen a goose that's been plucked, the skin has those same little dotted bumps all over it. Our skin does the same thing, so the name stuck. Not exactly the most flattering comparison, but hey, it's accurate. Here's another fun fact. Goosebumps are part of what's called the fight or flight response. When you get scared, your body pumps out adrenaline, which preps you for action. Faster heartbeat, sharper focus, muscles primed. Goosebumps sneak in as a leftover side effect of that adrenaline surge. Back in the day, a puffed-up, hairy body might have made you look more intimidating to predators. Today, the only thing intimidated is probably your date when they see your arm hairs standing at attention during a scary movie. But goosebumps aren't just about fear or cold. They can be emotional. Ever heard a song that gave you chills? Or listened to a speech that made the hair on your neck stand up? That's goosebumps too. Scientists think it happens because powerful emotions tap into the same ancient reflex. It's like your brain and your body briefly remembered they were once part of a survival machine, and they show it by giving you a full body shiver. So in short, goosebumps are a glitch in the evolutionary system. They're your body trying to warm you up or make you look fierce. But without the fur coat, they don't really succeed. All they do now is remind us we used to be hairier and maybe a little scarier.
The next time you notice goosebumps, you can think of them as a whisper from your ancient ancestors. They're like your body saying, "Hey, remember when we used to need this? Yeah, good times." And honestly, even though they don't do much now, there's something kind of cool about the fact that your skin still carries that old survival trick. It's like a time machine built into your body. So whether it's the cold air, a creepy story, or that one song that always hits you in the feels, goosebumps are just your body replaying a very old defense mechanism that doesn't really work anymore. A little useless, kinda awkward, but also pretty fascinating.
Why yawns are contagious. Did you just yawn? Or at least feel like you had to? Don't lie. Odds are you did. And if not, give it a few minutes because talking about yawning is almost guaranteed to trigger one. That's how powerful this thing is. But here's the question. Why? Why is yawning contagious? Why does seeing someone else yawn, hearing someone yawn, or even just thinking about yawning make you want to do it too? All right, let's start with the basics. What even is a yawn? For a long time, people thought yawning was about getting more oxygen into the body. You're tired, maybe you're not breathing deeply, so your brain tells you to take in a big gulp of air. Sounds nice and tidy, right? Except it doesn't fully check out. Studies show your oxygen levels don't really change much after a yawn. In fact, yawning seems more linked to things like brain temperature, kind of like a natural cooling system for your head. When you're bored or tired, your brain might be running sluggishly, so a yawn can reset things a little, like pressing a mini refresh button. But here's the fun part. Yawns aren't just about you, they're social. And this is where it gets wild. When you see someone else yawn, your brain has a sneaky little system that makes you copy them. That system is powered by something called mirror neurons. These are special brain cells that light up not only when you do something, but also when you watch someone else do it. It's like your brain is wired to mirror the actions of people around you. If you see someone smile, your brain gets nudged to smile. If you see someone scratch their arm, suddenly you feel itchy. And if you see someone yawn, yep, your brain says, hey, let's do that too. But why would evolution bother wiring us this way? Here's the cool theory. Contagious yawning helps with social bonding. Imagine you're part of a group of early humans. If one person yawns because they're tired and everyone else starts yawning too, the whole group ends up syncing their behavior. It's like a built-in way to keep everyone on the same rhythm. If the leader yawns and gets drowsy, the group might settle down to rest together. That's actually a survival advantage, being on the same page, sleeping at the same time, waking up at the same time. Safety in numbers, right? And it's not just humans who do this. Dogs catch yawns from their owners. Chimpanzees yawn when others in their troop yawn. Even some birds do it. The more social the animal, the more likely they are to catch yawns. That's a big hint that yawning isn't just about air or oxygen, it's about connection. Here's something even stranger. Contagious yawning seems tied to empathy. People who are more empathetic, that is, better at putting themselves in someone else's shoes, are more likely to yawn when they see others do it. Kids don't usually catch yawns until they're around 4 or 5, which is about the same age they start showing stronger empathy skills. And in people with conditions like autism, which can affect social processing, contagious yawning happens less often. That doesn't mean anything bad about the person, it just shows how yawning is tangled up with how our brains read social cues. And let's be real, it's kind of hilarious how unavoidable it is. Scientists have done experiments where they literally show people pictures of yawning faces, and within seconds the test subjects start yawning too. You can't fight it. Even reading the word yawn over and over again in this video might be messing with your head right now. I bet you've yawned at least once since we started, haven't you?
So to sum it up, yawns are contagious because our brains are wired to sync with each other. Mirror neurons make us copy what we see, and evolution probably kept that trait around because it helped groups stay connected and safe. Today, it's less about survival and more about, well, accidentally making your whole classroom or office yawn in unison. The next time someone yawns and you catch it, just know it's not weakness. It's proof that your brain is tuned into theirs. It's your body's way of saying, I see you, I feel you, and we're in this together. Weirdly enough, that makes yawning one of the simplest but most powerful examples of human connection.
Why you forget dreams so fast? Be honest, has this ever happened to you? You wake up in the middle of the night and you've just had the wildest dream. Like you were flying through a city made of spaghetti, or maybe you bumped into your old math teacher riding a dinosaur. It's crystal clear in your head. You're even telling yourself, I'll totally remember this in the morning. But then you wake up for real and poof, it's gone. All you're left with is a vague feeling, like you almost had it, but it slipped through your fingers. Why does that happen? Why are dreams so hard to hold on to, even when they feel so vivid while you're in them? The short answer: your brain basically puts a do not record sign on your memory system during dreaming. Let's break it down. Dreams mostly happen during a stage of sleep called REM sleep, which stands for rapid eye movement. That's when your brain is buzzing with activity, almost like it's awake. Your eyes dart around under your eyelids, your heart rate goes up, your breathing changes, and this is when the most intense and story-like dreams occur. But here's the twist. While your imagination is on overdrive, the part of your brain that normally stores long-term memories is kind of on vacation. That part's called the hippocampus. Think of the hippocampus as your brain's memory librarian. During the day, it helps take what's happening to you and files it away so you can recall it later. But during REM sleep, the hippocampus isn't working the way it usually does. Some researchers think this is because your brain is busy doing other maintenance tasks, like sorting and organizing your existing memories. So instead of recording your dream like a movie, your brain just lets it play without saving it to the hard drive. That's why you wake up and can barely remember what happened. It's not that you never encoded the dream, it's just that most of it never made it into long-term storage. Sometimes you get lucky and a piece slips through, especially if you wake up right in the middle of a dream. That's why people often remember their dreams better if they set alarms to wake themselves during REM sleep. Here's another fun detail. Dreams are also missing a sense of time and logic. Think about it. When you're dreaming, it feels normal for your grandma to suddenly turn into a talking cat, or for you to teleport from your bedroom to Mars without questioning it. That weird, this makes sense in the moment feeling happens because the prefrontal cortex, the part of your brain in charge of logic and decision-making, is mostly offline while you're dreaming. So not only are you failing to store the dream properly, but you're also experiencing it without the mental tools that would normally help you tag it as a memory worth keeping. Here's something else. Emotions play a big role in what you do or don't remember. If a dream is emotionally intense, say a nightmare that terrifies you, or a dream that makes you feel euphoric, you're more likely to remember it.
That's because strong emotions trigger the release of chemicals like norepinephrine, which can boost memory formation. It's like your brain saying, "Whoa, this mattered. Let's save it." That's why people often recall scary dreams better than the random ones where they're just grocery shopping in dreamland. But here's the kicker. Even if you think you've forgotten your dreams completely, tiny fragments often stick around in your subconscious. They can affect your mood, creativity, or even problem solving without you realizing it. Ever wake up in a bad mood for no reason? It might be a leftover from a dream you don't consciously remember. Or maybe you've had a random idea spark in the morning. It could have been planted by a dream your brain tossed away. And get this, people have trained themselves to remember more dreams. It's called dream journaling. The trick is to keep a notebook by your bed, and the moment you wake up, you jot down anything you can recall, even if it's just a weird color or a single word. Doing this regularly teaches your brain to pay more attention to dreams, and over time, you actually start to remember them more often. So, why do you forget dreams so fast? Because during REM, your brain is busy running the theater show of your imagination, but it forgets to hit the record button. The hippocampus isn't saving the files, the logic center is mostly offline, and only the emotionally charged scenes have a fighting chance of sticking around. Next time you wake up and lose a dream in seconds, don't feel bad. It's not your memory failing, it's just the way your brain is wired. Think of dreams like Snapchat messages, fascinating while they're happening, but designed to disappear almost immediately.
Why we hiccup. Okay, let's talk about one of those tiny but super annoying mysteries of the human body. Hiccups. You're just living your life, eating some noodles, laughing with a friend, maybe sipping on soda, and suddenly, hic, then again, and it doesn't stop. Everyone around you starts laughing, and you're there desperately trying to hold your breath or drink water upside down. But what actually is a hiccup, and why does it happen in the first place? The short version, a hiccup is your diaphragm, the big muscle under your lungs, throwing a mini temper tantrum. Here's what's going on inside your body. The diaphragm is the dome-shaped muscle that helps you breathe. When you inhale, the diaphragm contracts and moves downward, creating space for your lungs to fill with air. When you exhale, it relaxes and moves back up, pushing air out. It's a smooth, automatic process. But sometimes the nerves that control the diaphragm misfire. That's usually the phrenic nerve or the vagus nerve, which carry the breathe in, breathe out messages between your brain and diaphragm. When those signals go haywire, your diaphragm suddenly contracts at the wrong time. That quick, involuntary spasm forces you to suck in air, but right after that, your vocal cords snap shut. That's what makes the famous hic sound. So basically, diaphragm jerks, air rushes in, vocal cords slam shut, and you get a hiccup. Now, what triggers this weird glitch? A lot of things. Eating too fast, swallowing too much air, drinking carbonated beverages, sudden excitement, spicy food, alcohol, you name it. Anything that irritates your diaphragm or messes with the nerves can start the hiccup chain reaction. Sometimes it even happens when your stomach gets too full and pushes up against the diaphragm, like when you overeat at a buffet. But here's where it gets interesting. Scientists think hiccups might not just be random malfunctions. They might actually be leftovers from our evolutionary past. Yep, like a built-in software bug that we never fully deleted. One theory says hiccups are a remnant of an ancient breathing pattern from when our distant ancestors had gills.
Some amphibians, like tadpoles, use a breathing method that looks suspiciously like hiccups. They gulp water across their gills while closing a flap to keep it from going into their lungs. The nerve reflex that controls this looks very similar to what happens when we hiccup. So hiccups could be a leftover glitch from millions of years ago when our bodies were wired to handle both gill breathing and lung breathing. Kind of wild, right? Another theory is that hiccups may have once served a purpose in newborns. Babies hiccup in the womb a lot, sometimes for hours a day. Some scientists think it's like a training program for the baby's breathing muscles, helping them practice before birth. Once we grow up, though, we don't really need it anymore. But the reflex is still hanging around, waiting for the right trigger. Now, of course, we humans being humans, we've come up with about 1 million cures for hiccups. Hold your breath, drink water upside down, get scared by someone jumping out of the closet, stick sugar under your tongue, gargle with ice water. Some people swear by pulling on your tongue or pressing gently on your eyeballs. Sounds bizarre, but most of these tricks have one goal: to reset the nerves and muscles in your diaphragm so they stop spasming. And sometimes they work, sometimes they don't. Most hiccups are harmless and only last a few minutes. But here's a weird fact. In rare cases, people can get hiccups that last for days, weeks, or even years. The longest recorded case of hiccups? A guy named Charles Osborne hiccuped for 68 years straight. Can you imagine? His hiccups started in 1922 while he was weighing a hog on his farm and didn't stop until 1990. Doctors estimated he hiccuped about 430 million times in his life. That's both fascinating and horrifying. So why do we hiccup? On one level, it's just nerves misfiring and muscle spasming. On another level, it might be a little fossil of our evolutionary history, an echo of how ancient creatures used to breathe, or how babies practice breathing before they're even born. Either way, it's a reminder that not everything in the human body has a clear purpose anymore. Sometimes we just carry around these quirky leftovers, like hiccups, that are more funny than functional. Next time you get them, instead of just being annoyed, maybe take a second to think this little hic might be one of the oldest, weirdest reminders of where humans came from. And then, of course, try holding your breath, because let's be real, they're still super annoying.
Why your stomach growls when hungry. You're sitting in a quiet room, maybe a meeting, a classroom, or even a library, and suddenly, grrr, everyone hears it. You look down at your stomach like, really? Now? That low rumble is so unmistakable that people instantly know you're hungry. But here's the fun part. It's not actually your stomach tattling on you. Not exactly. The growling sound, officially called borborygmi. Yes, that's the real medical word. It sounds like a spell from Harry Potter. Comes from your intestines working hard even when they're empty. Here's the science. Your digestive system is never truly off. Even when you're not eating, your stomach and intestines go through regular cleaning cycles. Every couple of hours, your brain sends signals that trigger what's called the migrating motor complex, basically a wave of muscle contractions that sweeps through your digestive tract like a janitor cleaning the hallway after everyone leaves. These contractions push leftover food, mucus, and bacteria further down, making sure nothing just sits around and causes trouble. Now, when your stomach and intestines are mostly empty, these muscle squeezes push air and fluid around, and that sloshing movement creates those loud gurgling noises. It's kind of like shaking an empty water bottle. You hear way more noise than if it were full.
So why does it often happen when you're hungry? Because your body's smart. The same signals that start these contractions also stimulate hunger hormones, basically nudging you, hey, it's been a while since we ate. Time to refuel. The growls are like the background soundtrack to your body prepping itself for the next meal. Of course, the sounds can happen even if you're not hungry. If you've ever had your stomach growl right after eating, that's because digestion is still in progress. Food, liquid, and gas are moving along, making noise as they go. The difference is that when you're empty, the echoes are louder. No food muffling the sound means your intestines are basically playing percussion in your belly. Animals experience this too, but humans just notice it more because we sit in quiet rooms and feel embarrassed about it. Out in nature, nobody's judging a lion for having a rumbling stomach. Now, here's a quirky fact. Scientists think the loudness and frequency of your stomach growls can vary depending on your gut health, hydration, and even stress. Yep, your stress hormones can make digestion noisier by speeding up or slowing down those contractions. That's why some people get extra rumbles when they're nervous. So the next time your stomach growls loudly during an awkward silence, remember, it's not just random noise. It's your body's cleaning cycle at work. It's also your gut's way of keeping you alive and healthy by reminding you to eat. Basically, your stomach growling isn't a sign of weakness. It's proof your digestive system is on the job. And maybe, just maybe, it's the most ancient and honest form of communication your body has. No words, no filter. Just feed me.
Why airplanes leave white trails? You've probably looked up at the sky and noticed airplanes cruising along with long white streaks stretching behind them. Sometimes they fade quickly, sometimes they linger for hours, and sometimes the whole sky ends up crisscrossed with these lines like someone drew on it with chalk. And the big question is, what are those trails? Are they smoke, pollution, or, like conspiracy theorists love to say, chemtrails? Well, spoiler alert, nope. It's actually way simpler and way cooler. What you're seeing is just clouds forming. That's it. Here's the deal. Jet engines burn fuel, and just like your car, they produce exhaust. And one of the biggest things in that exhaust is water vapor. Now, way up where planes fly, usually around 30,000 to 40,000 feet, the air is freezing cold. We're talking minus 40 degrees C or even colder. At that temperature, water vapor doesn't stay vapor for long. So when hot, humid exhaust mixes with the icy air up there, that water vapor instantly condenses and freezes into tiny ice crystals. Those ice crystals are what you see as a white streak. In other words, planes don't paint the sky. They're just making little artificial clouds as they go. These streaks are officially called contrails, short for condensation trails. Now, here's where it gets interesting. Not all contrails are the same. Sometimes they disappear almost immediately, like a quick puff of breath you see on a cold day. Other times, they hang around for hours, slowly spreading out until they form thin sheets of cirrus-like clouds that cover big chunks of the sky. What makes the difference? The humidity up there. If the air is super dry, the ice crystals evaporate quickly, and the trail vanishes. If the air is already humid, those crystals stick around, grow, and spread because more water vapor condenses onto them.
That's why some days the sky is filled with streaks, and other days, nothing at all. Fun fact, pilots and meteorologists can actually use contrails to get a quick sense of conditions at cruising altitude. Persistent wide contrails usually means the upper atmosphere is moist, something weather nerds pay attention to because it can be a sign of incoming storms. And yeah, about those conspiracy theories, the idea of chemtrails, where people think planes are secretly spraying chemicals to control weather or people, is just not true. Everything about contrails is explained by plain old physics, chemistry, and atmospheric science. It's literally the same process as when you see your breath on a cold winter morning. The only difference is that instead of your mouth making vapor trails a few inches long, a jet engine is making trails miles long. So next time you look up and see those white streaks, you'll know you're basically watching high-altitude cloud making in action. It's not magic, it's not mystery, it's just science and really cold air. And honestly, there's something kind of poetic about it. Planes don't just take us from place to place, they also leave temporary signatures in the sky, little reminders of human flight etched across the heavens.
How Wi-Fi actually works. All right, let's talk about something you probably use every single day without giving it much thought. Wi-Fi. You're streaming videos, scrolling through memes, maybe even watching this video right now on Wi-Fi. But have you ever stopped and asked yourself, how is my phone literally pulling invisible internet out of thin air? Like, what is Wi-Fi actually doing? Is it magic? Is it sorcery? No, it's pure physics and engineering. And honestly, once you understand it, it feels even cooler than magic. So here's the deal. At its core, Wi-Fi is just radio waves. Yep, the same kind of invisible waves that carry music to your car radio or let you talk on a walkie-talkie. Wi-Fi doesn't use wires. It uses these electromagnetic waves to send information through the air. The trick is in how those waves are used. Think of the internet as just a huge amount of data, videos, text, pictures, cat memes. All of that boils down to binary code, ones and zeros. Every website, every message, every video you've ever streamed is just long strings of ones and zeros. So the job of your Wi-Fi router is to take those ones and zeros and turn them into tiny changes in radio waves. How? Well, Wi-Fi usually works in two main frequency ranges, 2.4 gigahertz and 5 gigahertz. That's insanely fast, billions of wave vibrations per second. Imagine a wave bouncing up and down billions of times in the blink of an eye. Now, by slightly tweaking the shape of these waves, changing their amplitude, the height, frequency, the speed, or phase, the timing, the router can encode whether it's sending a 1 or a 0. Your phone or laptop has an antenna inside it that listens for those patterns and decodes them back into binary code, which then turns into your TikTok video or Google search result. It's basically like Morse code on steroids. Instead of dots and dashes tapped out slowly by hand, Wi-Fi is blasting billions of microscopic changes every second. That's why it feels instant. You type a search, hit enter, and boom, answer delivered in milliseconds. Now, here's a cool thought. Wi-Fi isn't limited to sending info one way. Your phone also sends radio signals back to the router. That's how it tells the router, hey, I want to load this website, or play the next episode. So every time you use Wi-Fi, there's this invisible conversation happening between your device and your router way too fast for our brains to catch.
Of course, Wi-Fi isn't perfect. Radio waves can be blocked or weakened by walls, furniture, even your own body. That's why sometimes you step into the kitchen and suddenly your signal drops. It's literally the radio waves struggling to push through all the stuff in your house. That's also why we have Wi-Fi extenders or mesh networks to help spread those signals more evenly. And here's one more mind blower. Wi-Fi is getting faster because engineers keep finding smarter ways to cram more data into those waves. Newer Wi-Fi standards like Wi-Fi 6 and beyond use tricks like splitting channels, sending multiple signals at once, and reducing interference. So yeah, your router isn't just blasting random internet vibes. It's actually a very sophisticated little radio station sitting in your living room. So next time you're watching Netflix on your phone in bed, remember, that show isn't magically inside your device. Your router is shooting out crazy fast radio waves filled with ones and zeros. Your phone is catching them, decoding them, and reassembling them into video, all in real time. That's Wi-Fi. Invisible, silent, and lightning fast. And honestly, kind of mind-blowing once you think about it.
Why airplane turbulence happens. All right, let's talk about something that makes a lot of people grip their armrests a little too tightly. Airplane turbulence. You know the feeling. You're cruising at 35,000 feet, sipping your soda, scrolling your phone, and suddenly the plane jiggles like it just hit a pothole in the sky. Your stomach drops, the seatbelt sign dings, and everyone gets that wide-eyed look like, is this normal? Spoiler, it is normal, and it's way less scary when you actually understand what's happening. So here's the deal. Turbulence is basically just bumpy air. That's it. Imagine driving on a perfectly smooth highway. Your car glides along without a shake. But if you hit a rough patch of road, full of cracks or gravel, the ride gets bumpy. Planes work the same way, except the road they're traveling on is made of air. Now, even though we can't see it, air is constantly moving around in huge currents. Sometimes that movement is smooth, like a calm river. Other times it's chaotic, swirling, and messy, like rapids in a stream. When a plane flies through those uneven patches, it jiggles and bumps. That's turbulence. There are a few main causes. Jet streams. These are fast, narrow rivers of air, way up high in the atmosphere. Planes often fly near them to save fuel, but crossing in and out of a jet stream can create turbulence, like merging into traffic on a busy highway. Mountains. When wind smashes into big mountains, it has to go up and over. That creates invisible waves of air on the other side, almost like ripples in water. If your plane happens to cross through them, yep, turbulence. Thunderstorms and weather fronts. Big storm clouds are like giant air blenders, with warm air rising and cold air sinking. Planes avoid flying through storms, but even skirting around the edges can get bumpy. Clear air turbulence. This one's tricky because it happens in perfectly clear skies. No clouds to warn you. It's caused by invisible changes in wind speed and direction high up in the atmosphere. Pilots can't always see it coming, but they're trained to handle it. Now, here is the important part. Turbulence feels dramatic, but planes are built to handle way, way more than what you experience as a passenger. The wings, for example, they're designed to bend and flex, not snap. Engineers test them under extreme conditions that would make the average turbulence feel like a gentle shake. And pilots, they deal with it all the time. For them, turbulence is basically like driving over a speed bump. It might annoy you, but it's no big deal. What's really happening to you during turbulence is your body's sense of balance gets thrown off. Your inner ear expects smooth motion, and then suddenly the plane dips or jolts, and your brain goes, "Whoa, that's weird." That's why some people get nervous or even queasy. But rest assured, even when it feels intense, the plane isn't about to drop out of the sky. It's just riding out a patch of uneven air. So next time you're on a flight and the cabin shakes a little, picture it like this. Your plane is basically surfing waves in the sky. Sometimes the water is calm, sometimes it's choppy, but the board, aka the airplane, is built for it. Buckle up, take a breath, and remember, it's not dangerous, just bumpy.
Why batteries run out. Let's be real. Few things are as universally annoying as a dead battery. You're mid-scroll on your phone, mid-song in your headphones, or halfway through typing something important, and suddenly, bam, low battery warning, and then dead silence. But why do batteries even run out? Why can't we just keep recharging them forever? To get it, we need to peek inside what a battery really is. A battery isn't just some magic box that makes electricity. It's actually more like a little chemistry lab with carefully chosen ingredients inside. At its core, a battery is made up of two sides, the anode and the cathode. And between them, there's something called the electrolyte, which acts like a highway for tiny charged particles to move back and forth. When you turn on your device, what's really happening is a chemical reaction inside the battery. Atoms on one side start releasing electrons, tiny negatively charged particles. But electrons can't move directly through the electrolyte. Instead, they take the scenic route through your device. They travel through your phone or flashlight or laptop, powering it as they go, before eventually reuniting on the other side of the battery. That's the flow of electricity, a stream of electrons doing the work you need. But here's the catch. Those chemical reactions don't last forever. Every time the battery runs, it uses up a little bit of its fuel, which are basically reactive chemicals inside. Over time, you run out of easily available charge carriers, the stuff that can release or accept electrons. Once the reaction slows down too much, there aren't enough electrons flowing to keep your device alive, and the battery dies. Now, if you've got a rechargeable battery, like in your phone or laptop, you might be thinking, but hey, I just plug it in and it works again. What gives? Good question. What charging actually does is reverse the chemical reaction. You're basically forcing the used-up chemicals back into their original form, ready to go again. But here's the problem. It's not a perfect process. Every charge and discharge cycle wears things down a little. Some chemicals don't fully reset. Tiny bits of material break off inside, or the battery starts building up little resistances. That's why, after a year or two, your phone battery just doesn't last like it used to. Think of it like recharging a sponge. At first, the sponge soaks up water and squeezes it out perfectly, but after hundreds of squeezes, little tears form, fibers break, and the sponge doesn't hold as much as it once did. That's your battery over time. It still works, but it's just not as fresh as when it was brand new. And for non-rechargeable batteries, the ones you toss out after they die, those are built so that once the chemicals finish reacting, that's it. There's no way to easily reverse them. They're one and done, like a disposable coffee cup.
So the short answer to why do batteries run out is this: because inside, they're little chemical engines. They burn through their fuel molecule by molecule until there's not enough left to keep producing electricity. And while we've gotten really good at making batteries last longer and recharge better, they'll always have limits, because at the end of the day, chemistry is calling the shots. So next time your phone dies at 3% while you're out and about, don't think of it as your device betraying you. Just remember, there's a tiny science experiment inside that's been working hard all day, moving billions of electrons around just to keep you connected.
Why your phone heats up. You've probably noticed this. You're watching a video, gaming, or maybe scrolling endlessly through social media, and suddenly your phone feels like it's trying to cook your hand. It gets hot, sometimes even uncomfortably so. But what's really going on in there? Why does your phone heat up? The simple answer is because electricity isn't perfect. Every time energy moves through the circuits in your phone, some of it gets lost as heat. And since your phone is basically a tiny, powerful computer squeezed into a thin little rectangle, there's not a lot of room for that heat to escape. Let's break it down a little. Inside your phone, you've got a processor, kind of like the brain of the operation. This processor is doing millions, actually billions of calculations every single second. All those calculations are just electrons moving through circuits. And here's the thing, when electrons move, they don't glide effortlessly. They bump into things along the way, like atoms inside the metal wires. Every little bump creates resistance, and resistance equals heat. It's kind of like when you rub your hands together quickly. Friction makes warmth. So when your phone is crunching numbers non-stop, like when you're playing a game with fancy graphics or running apps in the background, it's generating more of that resistance, which means more heat. And it's not just the processor. The battery itself can be a big heat source. When your phone is charging fast or draining power quickly, the chemical reactions inside the battery speed up. And just like running hard makes your muscles warm, those reactions release heat too. Ever notice your phone gets hotter when you're charging and using it at the same time? That's the battery and processor both throwing a heat party. Another sneaky culprit? The screen. Especially on high brightness, your phone's display pulls a lot of power. That energy turns into light so you can see your screen, but again, no system is perfect. Some of that energy leaks out as heat. Now, you might wonder, okay, but why doesn't my phone have a fan like my laptop does? Well, it's all about space and design. Phones are made to be slim and portable, so instead of fans, they rely on clever engineering, like using metal frames to spread heat around, or software that slows down the processor if things get too hot. That's why sometimes your game suddenly lags or your phone feels slower. It's not broken, it's just protecting itself from overheating. And yes, in extreme cases, too much heat can actually damage a phone. That's why you'll sometimes see a warning that says the phone needs to cool down before you can use it. The device is literally saying, "Chill out, I'm overheating here." So next time your phone feels warm in your hand, it's not because it's working too hard in a human sense. It's just physics in action. Energy flowing through circuits, a little bit lost each time, showing up as heat. In a way, your phone heating up is proof of just how much work it's doing for you, all crammed into a tiny device that fits in your pocket.
how touchscreens know your finger is there. Think about it. You're scrolling through your phone, tapping out a message, or zooming into a picture, and the glass instantly knows exactly where your finger landed. No buttons, no pressure plates, just smooth glass, and yet it reacts perfectly. How does that even work? The secret is something called capacitive sensing, which is really just a fancy way of saying your body is part of an electrical circuit. Let's start super simple. Inside your phone's touchscreen is a hidden layer made of a grid, kind of like invisible graph paper, of super thin lines of a transparent material that conducts electricity. These lines crisscross to form thousands of little intersections. Each one can store a tiny bit of electrical charge, almost like a microscopic battery. Now, here's where you come in. Your body naturally carries a small electrical charge. It's not enough to shock someone like a cartoon villain, but it's there because your body is full of salty water. And salty water is great at conducting electricity. So when your finger touches the glass, it slightly changes the electrical field at that exact spot. Think of it like this. Imagine tossing a rock into a calm pond. The ripples spread out, right? When your finger touches the screen, it creates a little disturbance in the electrical pond. The system behind the screen instantly detects this disturbance and calculates exactly where it happened. That's why your phone doesn't react to, say, a plastic pen or a dry leaf. You need something that can conduct electricity to change the field. That's also why special styluses for touchscreens have conductive tips, so they pretend to be your finger. And here's another neat part. Touchscreens can sense multiple fingers at once because they're checking thousands of those little intersections in real time. That's how you can pinch to zoom or play games that use multiple touches at once. It's not magic. It's just a super fast computer constantly watching for those tiny electrical changes. Now, you might ask, okay, but what about those old school touchscreens where you had to press harder? Good catch. Those were resistive touchscreens, and they worked differently. They had two thin layers that touched each other when you pressed down, like squishing two sheets of plastic together. Modern capacitive screens don't need pressure. They just need the electrical signal from your body. That's why they feel smoother and way more responsive. And because capacitive sensing depends on electricity, that's also why your phone sometimes doesn't respond if you're wearing thick gloves. Your finger's charge can't get through. Unless, of course, the gloves are made with special conductive threads. So, the next time you're swiping through TikTok or typing away, remember, you're not just touching glass. You're actually completing a tiny invisible electrical handshake with your phone. And that's how it knows exactly where you are every single time.
Why elevators don't fall when cables snap. Okay, let's be honest. Who here has stepped into an elevator, looked around, and had that tiny voice in the back of their head whisper, "What if the cable snaps?" Yeah, pretty much everyone. It's one of those weird little fears that sticks with us, even if we don't say it out loud. The good news? That fear is basically unnecessary. Elevators have been designed to prevent that exact nightmare for over 150 years. So let's rewind to the 1800s when tall buildings were starting to pop up. Back then, elevators were mostly used for carrying goods, not people, because honestly, they weren't safe.
They were basically platforms hoisted by ropes, and yes, if the rope broke, everything came crashing down. Not exactly confidence-inspiring. Enter Elisha Otis, the guy who completely changed the game. In 1853, he stepped onto a platform high above a crowd at the New York World's Fair, and he gave a dramatic order. Cut the rope. The crowd gasped. People thought he was insane. But instead of plunging to the ground, the platform dropped just a few inches and then stopped. How? Otis had invented the safety brake. Here's how it worked. And honestly, it's brilliantly simple. Imagine the elevator car is attached to a spring-loaded set of metal jaws. As long as the rope or cable is holding the car up, those jaws are kept out of the way. But if the rope suddenly goes slack, the jaws instantly spring out and grab onto the guide rails along the elevator shaft, like a seatbelt locking in place during a sudden stop. That means the car doesn't fall, it just stays stuck in place. Modern elevators take this idea and make it even more advanced. First of all, the whole one cable idea is a myth. Passenger elevators typically have multiple steel cables, each strong enough to hold the car by itself. So for all the cables to snap at the same time, almost impossible. And even if that somehow happened, the safety brakes are still there, waiting to catch the car. There's also another clever system in place, the governor. No, not a politician. The governor is a mechanical device that detects if the elevator is moving too fast. If it senses the car is speeding downward faster than it should, it trips the safety brakes automatically. In other words, even if something weird happened, the elevator would still lock itself in place before hitting the bottom. And just to put your mind at ease even more, elevators are tested to extreme standards. They're loaded up with weights way heavier than you and I combined, and they're put through emergency stops to make sure those brakes always work. So the next time you step into an elevator and feel that little flicker of panic, just remember you're riding in one of the safest forms of transportation humans have ever built. Thanks to a guy in the 1800s who had the guts to literally risk his life in front of a crowd. Elevators don't fall when cables snap. Pretty wild, right?
Why glass can be both solid and liquid-like. All right, let me throw you a question. Is glass a solid, or is it a liquid? You'd think that's an easy one, right? You hold a glass cup, you knock on a window, you walk past a skyscraper made of glass panels. It's definitely solid. But then, you might have heard this weird fact floating around. Old cathedral windows are thicker at the bottom because glass slowly flows over centuries. So, which is it? Is glass some kind of frozen liquid that never quite hardened? Or is it just a normal solid like wood, metal, or stone? The answer is surprisingly strange. Glass is something in between. Scientists call it an amorphous solid, a solid that's structurally a bit like a liquid. Okay, let's break this down. Most solids you're familiar with, like salt, sugar, or metal, are crystalline. That means their atoms are arranged in a very neat, repeating pattern. Imagine a box of Lego bricks all stacked perfectly in rows. That's a crystal. The pattern repeats over and over, which is why crystals can form sharp edges and regular shapes. Liquids, on the other hand, are totally different. Their molecules are more like a messy crowd at a concert, jumbled, random, bumping around, not fixed in place. That's why liquids flow and change shape. Now, here's where glass is the oddball. If you zoom in on the atomic structure of glass, you won't find neat repeating rows like in crystals. Instead, the atoms are arranged more like a liquid's chaos, but frozen in place. It's like the concert crowd suddenly froze mid-dance. They're stuck, they can't move freely like a liquid anymore, but they're not organized like a true crystal either. That's why glass is called amorphous, which literally means without shape. It has the rigidity of a solid, you can't pour it, but the disordered structure of a liquid. It's basically a frozen liquid that never got the chance to crystallize. Now, let's go back to that myth about old church windows being thicker at the bottom because the glass flowed. Cool story, but it's not true. Glass doesn't actually drip or sag over centuries. The real reason those windows are uneven is because medieval glass-making techniques weren't very precise. Craftsmen made sheets of glass by spinning or rolling it, which left uneven thickness. When they installed the windows, they usually placed the heavier, thicker end at the bottom for stability. So no, your living room window isn't secretly oozing downward like honey in super slow motion. That said, there is a tiny kernel of truth to the idea that glass isn't as rigid as other solids. At very high temperatures, just below its melting point, glass doesn't go through a sharp snap from solid to liquid, like ice turning into water. Instead, it gradually softens. Scientists call this the glass transition. It's more like bread dough slowly loosening up than ice suddenly melting into water. That slow, gradual change is part of why glass seems mysterious compared to most solids. Another cool thing, because glass is amorphous, it has some weird properties. For example, it doesn't have a clear melting point. It also tends to break in unpredictable ways. Ever notice how a shattered window doesn't split into neat cubes, but into long, sharp shards? That's because there's no repeating crystal structure to dictate the break lines. On the flip side, tempered glass, which you find in car windows or phone screens, is specially heat-treated so it shatters into tiny pebble-like pieces instead of deadly knives. And here's a fun twist. Scientists still debate whether glass is a true solid at all, or if it should be classified as an extremely slow-moving liquid. The reality is, at room temperature, glass molecules are locked in place so tightly that it would take longer than the age of the universe to see them move. So for all practical purposes, your cup, your window, your sunglasses, it's solid. So what's the takeaway here? Glass doesn't neatly fit into the solid or liquid categories we learned about in school. It's an amorphous solid, rigid like a solid, disordered like a liquid, and mysterious enough to spark myths about it flowing over time. The next time you look out a window, remember, you're staring through one of the strangest states of matter we deal with every day. Pretty wild for something we'd literally clean with Windex, huh?
Why streaming doesn't buffer like old videos. All right, let's hop back in time for a second. Do you remember the early days of watching videos online? You'd click play, and before anything happened, that little spinning wheel or progress bar would taunt you. Buffering? Sometimes it would stop halfway through your video and freeze, leaving you staring at a pixelated still frame while the audio cut out. Painful, right? But fast forward to today. You open Netflix, YouTube, or Disney+, hit play, And boom, the video just starts. Even if your internet isn't great, the video might drop in quality for a moment, but it rarely stops completely. No more eternal buffering circles. So what changed? The magic behind this smoother experience is something called adaptive bitrate streaming. Sounds technical, but I promise you'll get it by the end of this explanation. Let's start with the old days. Back then, videos were usually downloaded or streamed at one fixed quality. Say you wanted to watch a 720p video. The system would try to send you the whole video at that resolution, no matter what your internet connection was doing. If your internet speed suddenly dipped, boom, buffering. The video would pause while your device tried to catch up. It's kind of like ordering food delivery from a single fancy restaurant far away. If the driver gets stuck in traffic, you're just sitting there hungry with no food. No alternatives, no adjustments, just waiting. Now here's where adaptive bitrate streaming changes the game. Instead of locking you into one version of the video, modern streaming platforms actually store multiple versions of the same video at different quality levels. So your favorite show might exist in 240p, 480p, 720p, 1080p, and even 4K, all ready to go. When you hit play, your device and the streaming service start a little back-and-forth conversation. The player checks, hey, how fast is this person's internet right now? How much can I handle without stalling? Based on that, it chooses the right quality level on the fly. And here's the genius part. It doesn't just make this decision once at the start. It keeps checking every few seconds. If your internet suddenly slows down, maybe someone else in the house starts a big download, the stream instantly drops to a lower quality to keep playing smoothly. And if your connection improves again, it bumps you back up to high quality automatically. That's why sometimes you'll notice a video looking a little blurry for a minute, then sharpening up again. It's not your eyes. It's adaptive streaming quietly adjusting in the background so you don't have to sit through buffering. To make this work, videos are chopped into tiny chunks, usually just a few seconds long. Each chunk is available in multiple qualities. Your device picks which chunk to request based on current conditions. Think of it like having a buffet of food ready in small plates. If your appetite, internet speed, is small, you grab the lighter plates. If it suddenly grows, you grab the bigger plates. Either way, you're still eating, no waiting around. This method became the standard thanks to protocols like HLS from Apple and MPEG-, which basically set the rules for how these little video chunks are served up. Today, pretty much every major streaming service uses some version of this. Let's put it in human terms. Adaptive bitrate streaming is like having a smart waiter who notices if you're eating slowly or quickly. If you're struggling, they bring you smaller bites so you don't choke. If you're zooming through your meal, they speed things up with bigger portions. Either way, the meal keeps flowing, and you never sit there with an empty plate. Now, you might ask, why not just always stream at the highest quality? Well, two reasons. First, not everyone has the internet speed to handle full 4K without constant buffering. Second, even if you could, your internet might fluctuate. Streaming has to be smart enough to deal with those ups and downs in real time. That's also why services let you pick auto quality. Behind the scenes, auto just means let adaptive streaming do its thing and give me the best quality my connection can handle right now. And if you've ever wondered why sometimes a video starts off looking a little blurry, then clears up after a few seconds, that's deliberate too. The system starts with the lower quality version to get the video playing instantly. Then, as it confirms your connection is steady, it smoothly upgrades you. The idea is, it's better to start watching right away in a slightly lower quality than to sit staring at a spinning wheel. So the next time you're binge watching and notice the video looks crystal clear one moment, then a little soft the next, don't worry,
That's not your internet failing you. It's actually your streaming service saving you from the dreaded buffering screen. In short, old videos buffered because they streamed in one fixed quality. Today's videos adjust in real time using adaptive bitrate streaming. Your device constantly negotiates with the server to give you the smoothest playback possible, even if it means dropping quality for a moment. Pretty cool, right? The tech that keeps your favorite shows flowing smoothly isn't just about faster internet, it's about smarter delivery. And honestly, I'll take a few seconds of blurry video over that eternal spinning wheel any day.
How noise-canceling headphones actually cancel sound. Picture this. You're sitting on a plane, engines roaring so loudly you can barely think. You put on your fancy noise-canceling headphones, press that little button, and suddenly the roar fades into a gentle hum, almost like magic. But here's the kicker. It's not magic, it's physics. Specifically, something called inverse wave interference. Sounds complicated? Don't worry. By the end of this, you'll not only understand it, you'll be able to explain it to your friends like a pro. Let's start with the basics. Sound is just waves of pressure moving through the air. Imagine the air as a calm ocean. When you clap your hands, it's like dropping a stone in the water. You create ripples, or waves, that spread outward. Those ripples are sound waves, and your ears are the sensors picking them up. Now, every sound wave has peaks, where the air is squished together, and troughs, where the air is spread apart. When these waves reach your ears, your brain interprets them as sound. Simple enough. Here's where the magic of noise cancellation comes in. What if instead of just letting those sound waves hit your ears, you could create a new wave that perfectly cancels them out? That's exactly what noise-canceling headphones do. They have tiny microphones built right into the ear cups. These microphones are always listening to the noise around you, like the engine hum on that plane or the chatter in a coffee shop. Then, using a super fast processor, the headphones generate a sound wave that's the exact opposite of the noise. Think of it like this. If the noise wave has a peak, the headphones create a trough. If the noise wave has a trough, the headphones create a peak. When you combine them, bam, they cancel each other out. The ocean goes flat again. Silence. This is called destructive interference. Two waves that are mirror images of each other meet, and instead of doubling the noise, they erase it. Here's a fun analogy. Imagine two kids jumping on a trampoline. One kid jumps up while the other jumps down at the exact same time. If they sync perfectly, they cancel each other's movement and the trampoline stays flat. That's essentially what's happening in your ears with noise-canceling headphones. Now, this all sounds straightforward, but the tricky part is timing. The headphones have to react almost instantly. If the anti-noise wave comes even a split second too late, instead of canceling the sound, it just adds more chaos. That's why the processors inside these headphones are working at lightning speed, measuring the sound, flipping it, and playing it back in real time. There are actually two kinds of noise cancellation. The first is passive noise cancellation, which is just fancy talk for good old-fashioned earmuffs. Thick padding around the headphones physically blocks outside sound, like putting your fingers in your ears. That helps with higher-pitched noises, like chatter or clinking dishes. But the real magic is active noise cancellation, or ANC. That's that inverse wave trick we've been talking about. It's especially good at canceling out low, steady sounds like airplane engines, train rumbles, or the hum of an air conditioner. Those are the types of sounds where the wave pattern is predictable, so the headphones can generate a perfect opposite.
This is why if you've used noise-canceling headphones before, you may notice they don't completely erase sudden sounds, like someone clapping or shouting. Those noises are too quick and irregular for the system to predict and cancel in time. Instead, ANC shines at wiping out the droning, repetitive sounds that normally wear you down over hours. Now, you might be wondering, if the headphones are generating extra sound waves to cancel noise, doesn't that mean they're actually making more noise? Technically, yes. But because that sound is precisely engineered to be the inverse of the unwanted noise, your brain perceives silence instead. It's a little like fighting fire with fire, but in this case, it's fighting sound with sound. Some newer headphones even go a step further. They use adaptive ANC, which means they're constantly adjusting to your environment. Walking on a busy street, they tweak the cancellation to handle car engines. Sitting in a library, they ease off so you can still hear someone whispering your name. It's like having a sound engineer inside your headphones, constantly fine-tuning things for you. Here's another little fun fact. The concept of noise cancellation isn't new. The idea of using sound waves to cancel other sound waves was first proposed way back in the 1930s. But the technology to make it practical in consumer devices didn't arrive until much later, when microprocessors and tiny microphones became powerful enough to keep up with real-world noise. So the next time you put on noise-canceling headphones and feel that peaceful hush descend around you, remember, it's not sorcery, it's science. Your headphones aren't literally listening to the world, flipping the sound upside down, and feeding it back to you so perfectly that your ears think the noise disappeared. To sum it up, sound is just waves. Noise-canceling headphones use microphones to detect those waves. They generate opposite waves, mirror images, that cancel the noise. This works best on steady, low-frequency sounds, like engines or hums. Sudden noises still sneak through, but the headphones massively reduce overall background noise. And that's why you can sip your coffee in peace at a noisy cafe, lost in your music, while the chaos of the world fades into the background.